Good evening and welcome to the Late Lab. I'm very glad you've joined me. Before we settle into tonight's subject, let me know where in the world you're listening from. Perhaps you're tucked beneath the covers, watching the lights pass by from a late-night train, or resting somewhere quiet with the day finally behind you. Wherever this finds you, I hope the room feels peaceful, the evening feels gentle, and you can let your thoughts wander without needing to hurry anywhere. These slow explorations are made for nights exactly like this, and if you enjoy them, leaving a like or subscribing is a simple way to help the Late Lab continue growing. And to everyone who has already subscribed, thank you for returning. It genuinely means a great deal to have you here. Tonight, we're stepping into one of the most famous ideas in quantum physics, although it is also one of the most frequently misunderstood. I'll do my best to keep it relaxing, even as we ask whether nature is genuinely uncertain, whether we simply lack the right information, or whether the question itself stops making sense at the quantum scale. So, make yourself comfortable, and let's ease into it. What does quantum uncertainty actually mean? And why, almost a century after Werner Heisenberg introduced it, are physicists still arguing about what it tells us about reality? Quantum uncertainty is one of the strangest examples of certainty in modern science. The mathematics behind it has been tested repeatedly in experiments involving light, electrons, atoms, neutrons, molecules, and superconducting circuits. The predicted spreads in measurement results appear with remarkable consistency. They do not vanish when instruments improve or laboratories become quieter. As far as modern physics can tell, quantum uncertainty is not a temporary inconvenience waiting for better equipment, and yet physicists still argue about what it actually means. That may sound contradictory. If the equations work and the experiments agree with them, what is left to debate? Quite a lot. The difficulty begins with the word uncertainty. In ordinary life, uncertainty usually means that something has a definite answer, but we do not know it. A card lies face down on a table. It is already one particular card, even if nobody has looked. In this familiar case, the uncertainty belongs to us. It reflects missing information. Quantum mechanics allows a different possibility. A quantum state may be prepared so that repeated measurements do not all produce the same result. Instead, they form a probability distribution. The spread is not necessarily caused by careless preparation or a faulty detector. It may be built into the state itself. This is known as preparation uncertainty. Imagine preparing many electrons in the same way. Position is measured for one group, while momentum is measured for another. Even with accurate instruments, the two distributions cannot both be made arbitrarily narrow. A state confined to a small region of space must possess a wider range of possible momenta. A state with sharply defined momentum must be spread more widely across position. Position tells us where something may be found. Momentum describes the amount and direction of its motion. In classical physics, an object can possess an exact position and an exact momentum at the same time. Quantum mechanics does not permit a state in which both probability distributions are perfectly sharp. This is the famous position and momentum uncertainty relation, usually associated with Werner Heisenberg. It is also where several different ideas are often pushed beneath one convenient label. One statement says that we cannot know both quantities precisely. Another says that the particle does not possess precise values for both before measurement. A third says that measuring position physically disturbs momentum. A fourth says that no apparatus can measure both together with unlimited accuracy. These claims are related, but they are not the same. Saying that we cannot know a value is a claim about knowledge. Saying that a particle has no definite value is a claim about physical reality. Saying that measurement changes the particle is a claim about interaction. Saying that an apparatus has limited accuracy is a claim about experimental operations. Popular explanations often blend all four together, rather like putting several different keys on the same ring and assuming they must open the same door. Measurement error is one source of uncertainty. Every real instrument has finite resolution, a detector may produce a reading slightly different from the quantity it is meant to measure. Better engineering can often reduce this kind of uncertainty. Measurement disturbance is different. To measure a quantum system, an apparatus must interact with it. A photon may scatter from an electron, or a magnetic field may separate atoms according to spin. The interaction can alter the state and change the probabilities for a later measurement. Werner Heisenberg illustrated this with a microscope. Short wavelength light could locate an electron more precisely, but the photon would also transfer momentum to it. The position measurement would disturb the motion. This picture is useful, but it is not the whole uncertainty principle. The most familiar mathematical relation concerns the statistical spread already present in a quantum state. It applies even when nobody tries to measure position and momentum one after the other. The microscope describes measurement backaction. The standard relation describes the structure of quantum states. Treating them as identical has created nearly a century of confusion. Quantum uncertainty also reaches beyond position and momentum. Different components of spin obey uncertainty relations. Spin is an intrinsic quantum property related to angular momentum, not a tiny ball literally rotating in space. A state with one precisely defined spin component will generally produce uncertain results for another incompatible component. Phase and particle number can display a similar trade-off, with a sharply defined particle number associated with a less definite phase. Physicists describe such pairs as incompatible observables. The mathematical operations representing them do not commute, meaning their order matters. This structure prevents one quantum state from assigning arbitrarily sharp distributions to both observables at once. But the mathematics still leaves room for interpretation. Perhaps the wavefunction completely describes reality, and some properties do not possess definite values before measurement. Perhaps it describes information rather than the world itself. Perhaps hidden variables exist beneath the quantum state, although experiments place severe restrictions on them. Perhaps every possible outcome survives in a branching quantum reality. Or perhaps properties become definite only relative to particular interactions. The equations set strict limits, predict probability distributions, and tell laboratories what correlations to expect. What they do not provide, without interpretation, is one universally accepted picture of what an individual quantum system is doing between preparation and measurement. That is the certainty hidden inside quantum uncertainty. The rules are dependable. The evidence is extraordinarily strong. The disagreement begins when we ask what those successful rules are actually describing. Is uncertainty incomplete human knowledge? Is it an unavoidable spread in physical properties? Is it a limitation on what measurements can reveal together? Or is it something deeper about which properties can exist simultaneously? Quantum mechanics answers the calculations with confidence. It is the meaning of those answers that remains uncertain. For most of human history, uncertainty meant something simple. The world had definite properties, but people did not always know what they were. A leaf drifting through the air has a particular position at every moment. It also has a particular speed and direction, even if nobody is watching closely enough to record them. Its path may appear irregular as it turns, rises, and falls, but the classical explanation is straightforward. The leaf is being pushed by moving air, pulled downward by gravity, and affected by countless small differences in shape, moisture, and turbulence. The motion is difficult to predict because the necessary information is missing. It is not assumed to be undecided. The same principle applies to a ball rolling across a floor. Given its starting position, its speed, the direction of its motion, the slope of the surface, and the strength of friction, its later position can be calculated. A poor prediction usually means that one of those quantities was measured inaccurately, overlooked entirely, or simplified too aggressively. Even the motion of a distant planet follows this classical pattern. Astronomers may not know its orbit perfectly at first, but the planet is still presumed to occupy a definite location and move with a definite momentum. better observations improve the prediction because they reduce ignorance about a reality that already exists. This view became extraordinarily powerful through the work of Isaac Newton. Newton's laws of motion described how forces change the movement of physical objects. His law of universal gravitation connected falling objects on Earth with the motion of the Moon and planets. The same basic rules could describe an apple descending from a tree and a world travelling around the Sun. Within Newtonian mechanics, the future state of a system is determined by its present state. If the position and momentum of an object are known, and every force acting upon it is specified, its later motion can in principle be calculated. This does not mean that every calculation is easy. It means that the laws themselves do not introduce fundamental randomness. A tossed stone does not pause in midair to consider several possible trajectories. It follows one path. A planet does not select an orbit from a probability distribution each morning. It continues according to its motion and the gravitational forces surrounding it. This deterministic picture reached its most ambitious form in the ideas of Pierre-Simon Laplace. Laplace imagined an intelligence with complete knowledge of nature. It would know the position and momentum of every particle, along with every force acting throughout the universe. With unlimited calculating ability, it could use the laws of physics to reconstruct the entire past and predict the entire future. This imagined intelligence later became known as Laplace's demon. It was not meant to be a mischievous supernatural creature hiding behind the planets with an alarming collection of notebooks. It was a philosophical symbol of perfect knowledge. For Laplace's intelligence, nothing would be uncertain. The motion of every molecule, the formation of every cloud, and every future event would follow from the exact state of the universe at one moment. Human beings could not perform such calculations, of course. We lacked both the information and the computational power. But that limitation belonged to us, not to nature. This distinction remains important because a system can be practically unpredictable without being fundamentally indeterminate. Weather provides a familiar example. The atmosphere contains immense numbers of moving molecules. Air pressure, temperature, humidity, wind speed, cloud formation, ocean currents, sunlight, and the shape of the land all influence its development. Tiny differences in initial conditions can grow into much larger differences over time. This sensitivity is associated with chaos theory. It means that even a small measurement error can eventually lead to a very different forecast. A weather prediction may therefore become unreliable after a limited period, but classical unpredictability does not necessarily imply that the atmosphere has no definite state. It may simply mean that the relevant state is too complex to measure and calculate with perfect accuracy. Probability was already useful in physics long before quantum mechanics appeared. James Clerk Maxwell used statistical methods to describe the speeds of molecules in a gas. Ludwig Boltzmann developed statistical mechanics further, connecting the microscopic behavior of atoms and molecules with macroscopic quantities such as temperature, pressure, and entropy. Josiah Willard Gibbs created a broad mathematical framework for describing large collections of possible microscopic states. A container of gas may hold an unimaginably large number of molecules. Tracking every collision would be wildly impractical. Statistical mechanics avoids that impossible task by describing distributions and averages. It can predict the pressure of the gas without identifying the exact location and velocity of each molecule. It can explain temperature as a measure connected to microscopic motion. It can describe why heat tends to spread from warmer regions into cooler ones. Probability was essential, but it was interpreted as a practical tool. Each molecule was still assumed to possess a definite position and momentum. The probability distribution represented the observer's incomplete knowledge of those values. Beneath the statistics, the classical world remained precise. This was the intellectual background into which quantum mechanics arrived. When early quantum physicists began encountering unavoidable probability distributions, it was natural to assume that some deeper description must be missing. Perhaps electrons and photons possess definite properties hidden beneath the mathematical wave function. Perhaps quantum probabilities were temporary signs of an incomplete theory, just as the probabilities of statistical mechanics reflected ignorance about individual molecules. The alternative was far more unsettling. Quantum theory seemed to suggest that probability might not merely describe what physicists fail to know. It might be part of the most complete description available. Albert Einstein found this possibility difficult to accept. He recognized the extraordinary success of quantum mechanics, but doubted that its probabilistic character represented the final level of reality. He suspected that a deeper theory might restore a more complete account of individual physical systems. This expectation later inspired hidden variable theories, which attempt to explain quantum probabilities through additional properties not included in the ordinary wave function. The question was no longer whether human beings sometimes lacked information. That had always been obvious. The deeper question was whether the information existed in a definite form at all. By the end of the 19th century, physics seemed to have divided nature into two comfortably separate categories. Matter was made from particles. A particle occupied a particular place, moved along a definite path, and carried properties such as mass, speed, and momentum. Its motion might be complicated, but it was still motion along a trajectory. Light, sound, and ripples on water belonged to the other category. They were waves, extended across space rather than concentrated at one point. A wave could bend around obstacles, overlap with another wave, and produce patterns of interference in which peaks reinforced one another or cancelled one another out. The distinction appeared clear. Particles travelled like tiny objects. Waves spread like disturbances. Nature, however, was about to become less cooperative. One of the first serious cracks appeared in the study of black-body radiation. A black body is an idealized object that absorbs all electromagnetic radiation falling upon it and emits radiation according to its temperature. Real objects are not perfect black bodies, but heated cavities can approximate the behavior closely enough to reveal the underlying physics. Experiments showed a very specific distribution of emitted light. Classical calculations could describe part of that distribution, but they failed badly at short wavelengths. The theory predicted that a heated object should release an unlimited amount of energy in the ultraviolet region. This absurd result became known as the ultraviolet catastrophe. Real ovens, thankfully, do not produce infinite ultraviolet radiation while preparing dinner. In 1900, Max Planck found a mathematical solution. He proposed that the walls of a heated cavity could exchange energy with electromagnetic radiation only in discrete amounts. The permitted amount depended on the frequency of the radiation and on a new fundamental constant, now called Planck's constant. In spoken form, the central relationship can be expressed as the energy of one quantum equals Planck's constant multiplied by the frequency. Planck initially treated this quantization cautiously. It was a way to reproduce the observed spectrum, and he did not immediately insist that light itself existed as separate particles. Even so, the proposal introduced a startling idea. Energy might not always be exchanged in a perfectly smooth continuum. At very small scales, nature appeared to count. Albert Einstein pushed the idea much further in 1905. He examined the photoelectric effect in which light striking certain materials causes electrons to be released. Classical wave theory suggested that bright light should eventually provide enough energy to eject electrons regardless of its colour. Experiments showed something different. Below a particular frequency, no electrons were released, even when the light was made intense. Above that threshold, electrons appeared almost immediately. Increasing the frequency increased the energy of the emitted electrons, while increasing the brightness mainly increased their number. Einstein proposed that light behaves as if its energy is concentrated into individual quanta. Each light quantum carries an amount of energy determined by its frequency. One electron generally absorbs one quantum. If that quantum does not carry enough energy to escape the material, simply adding more low-frequency light does not solve the problem. This was a direct challenge to the idea that light was only a continuous wave spread smoothly through space. Light still produced interference and diffraction, unmistakably wave-like behaviour. Yet in the photoelectric effect, it transferred energy in localised packets. The neat division between particles and waves had begun to dissolve. Atoms presented another difficulty. According to classical electromagnetic theory, an electron travelling around an atomic nucleus should radiate energy, spiral inward, and collapse into the nucleus extremely quickly. Stable matter should not exist for long enough to become anyone's problem, let alone form planets, tea, and laboratories. In 1913, Niels Bohr proposed an atomic model in which electrons were restricted to particular energy states. They could move between these states only by absorbing or emitting specific amounts of energy. The frequencies of the emitted light matched patterns observed in atomic spectra, especially for hydrogen. Bohr's model was remarkably successful in certain calculations, but it left a deep mechanical mystery. Why were only particular orbits allowed? What exactly prevented an electron from occupying the spaces between them? The model stated the rules without fully explaining the underlying behaviour. The situation became stranger when Louis de Broglie suggested in 1924 that matter might possess wave properties. De Broglie proposed that a particle's wavelength is related to its momentum. In clear-spoken form, the relationship is the wavelength of a particle equals Planck's constant divided by the particle's momentum. An electron, on this view, was not merely a tiny object following a miniature planetary orbit. It could also be associated with a wave. The allowed states in an atom could then be understood as standing wave patterns, rather like vibrations that fit neatly along a string while other patterns cancel themselves out. This connected the discrete energy levels of atoms with wave behaviour, but it also prepared the way for uncertainty. A wave with one perfectly defined wavelength extends indefinitely through space. It has no sharply defined beginning or end. Because wavelength is related to momentum, a wave with one exact wavelength corresponds to one exact momentum, but it cannot be confined to one precise location. To create something localized, many waves with slightly different wavelengths must be combined. Their peaks can reinforce one another within a limited region and cancel outside it, producing a wave packet. The price of localization is therefore a range of wavelengths, and because different wavelengths correspond to different momenta, a sharply localized packet must contain a spread of possible momenta. This was not yet the complete uncertainty relation, but the essential trade-off was already present in the structure of waves. A state could be narrow in position or narrow in momentum, but not arbitrarily narrow in both. Erwin Schrödinger developed wave mechanics in 1926, providing an equation that described how a quantum wave changes over time. The resulting wave function could represent electrons in atoms, particles moving through space, and many other quantum systems. At first, it was tempting to imagine the wave function as a physical wave of matter, but this interpretation encountered serious difficulties. When an electron was detected, it did not arrive as a thin mist spread across the entire detector. It appeared at one localized point. Max Born proposed the interpretation that became central to quantum mechanics. The wave function itself was not simply a material substance. Its magnitude determined the probability of finding a particular measurement result. More precisely, the square of the magnitude of the wave function gives the probability density for a measurement outcome. The quantum wave therefore did not predict one definite trajectory in the classical sense. It assigned amplitudes to multiple possible outcomes. When many identically prepared systems were measured, those amplitudes determined the statistical pattern that appeared. Uncertainty was no longer an extra restriction imposed after the theory had described a perfectly definite particle. It emerged naturally from the form of the quantum state itself. A wave function spread across position predicted a distribution of possible positions. A wave function containing several momentum components predicted a distribution of possible momenta. the classical particle with one hidden path had been replaced, at least within the standard formalism, by a state of amplitudes and probabilities. The calculations worked. The deeper meaning remained unsettled. Did the wave function describe a real physical object spread through space? Was it only a catalogue of human knowledge? Did it represent objective possibilities waiting to become definite? Or was it simply a mathematical device for predicting what an experiment would reveal? Max Born had transformed the wave into probability. He had not settled. What, exactly, the probability was a probability of? The arrival of wave mechanics made quantum behaviour easier to picture, but it was not the first complete mathematical form of quantum mechanics. A year before Erwin Schrödinger published his wave equation, Werner Heisenberg had approached the problem from a very different direction. In 1925, Heisenberg was trying to describe the behaviour of electrons inside atoms. The familiar picture showed electrons travelling around a nucleus along definite paths, rather like planets orbiting the Sun. Yet those supposed paths could not be observed directly, and classical calculations based upon them repeatedly failed to reproduce the properties of real atoms. Heisenberg decided to stop building the theory around invisible trajectories. Instead, he focused on quantities that could be connected to experiments. Atoms absorb and emit light at particular frequencies. Those frequencies reveal transitions between discrete energy states. The intensity of each spectral line provides information about the strength or likelihood of a transition. Rather than asking where an electron was at every instant, Heisenberg constructed mathematical arrays describing possible transitions from one atomic state to another. This was a radical change in emphasis. Classical mechanics normally begins with an object moving through space, and then calculates what an observer will measure. Heisenberg began with observable patterns and built the theory around the relationships between them. The arrays he produced were complicated, and Heisenberg did not initially recognize the familiar branch of mathematics they belonged to. Max Born examined the work and realized that the quantities followed the rules of matrices. A matrix is an organized rectangular array of numbers or mathematical expressions. Matrices can represent transformations, relationships, and linked sets of quantities. They had existed in mathematics for decades, but physicists had not expected them to become the natural language of atoms. Max Born worked with Pascal Jordan to develop Heisenberg's method into a more systematic theory. Werner Heisenberg, Max Born, and Pascal Jordan then extended the framework further in a major joint paper. The resulting approach became known as matrix mechanics. Its predictions agreed with the later wave mechanics of Erwin Schrödinger. Although the two theories looked completely different at first, Schrödinger and others showed that they were mathematically equivalent forms of quantum mechanics. Matrix mechanics revealed something that would become central to quantum uncertainty. In ordinary arithmetic, the order of multiplication usually makes no difference. 3 multiplied by 5 gives the same result as 5 multiplied by 3. Many familiar physical operations behave in a similarly cooperative manner. Imagine moving a book 2 meters to the right and then 3 meters forward. Reversing the order still leaves the book in the same final position. The route changes slightly, but the result does not. Some operations do depend on order. Rotations provide a simple example. Turning an object around one axis and then another can leave it facing a different direction from the result produced when the rotations are reversed. Matrices often share this order dependence. Multiplying one matrix by another does not generally produce the same result when their order is exchanged. Quantum observables inherit this property. An observable is a measurable physical quantity represented within quantum mechanics by a mathematical operator. Position is one observable, momentum is another. Energy, angular momentum, and spin components are also observables. An operator acts upon a quantum state and helps determine the possible measurement results and their probabilities. When the position operator and momentum operator are applied in one order, the result differs from what is obtained when their order is reversed. Position followed by momentum is mathematically different from momentum followed by position. Physicists describe such observables as non-commuting. The word commuting may sound as though position and momentum are waiting together for a train, but it comes from the idea of exchanging order. Two operations commute when swapping their order makes no difference. They fail to commute when that exchange changes the outcome. The amount by which two operators fail to commute is described by their commutator. The commutator is formed by applying the first operator followed by the second, then subtracting the result obtained in the reverse order. If the difference is zero, the operators commute. If it is not zero, their mathematical order matters. For position and momentum, the relationship can be stated as the commutator of position and momentum equals the imaginary unit multiplied by the reduced Planck constant. The imaginary unit is a mathematical quantity whose square equals -1. The reduced Planck constant is Planck's constant divided by 2 multiplied by pi. It sets the characteristic scale of quantum effects and is extraordinarily small in ordinary human units. The smallness of the reduced Planck constant helps explain why the non-commuting structure of quantum observables is not obvious when dealing with footballs, falling leaves, or planets. At atomic scales, however, it cannot be ignored. This relationship is not a statement about a damaged instrument or an experimenter lacking patience. It belongs to the mathematical structure of quantum mechanics itself. Even with a perfectly designed apparatus, position and momentum are represented by operators that do not commute. Their incompatibility is present before the practical details of any laboratory measurement are considered. This is also why non-commutation should not be reduced to the simple idea that measuring one quantity physically knocks the other out of place. Measurement disturbance is real and important, but operator non-commutation is more fundamental. It describes the relationship between the observables and the quantum state, whether or not a particular measurement has yet occurred. Suppose a quantum state has a perfectly defined position. In the mathematical language of quantum mechanics, it is then an eigenstate of the position operator. Measuring position would return the corresponding value with certainty. That same state cannot generally be an eigenstate of momentum. Instead, a momentum measurement would produce a distribution of possible results. The reverse is also true. A state with one perfectly defined momentum is spread throughout position space and cannot possess one sharply defined position. This mathematical incompatibility is the foundation beneath the familiar uncertainty relation. A quantum state cannot normally be made arbitrarily narrow for two non-commuting observables at the same time. The same pattern appears elsewhere in quantum physics. Angular momentum has different components associated with different spatial directions. The component along one direction does not commute with the components along the other two directions. A state may have a sharply defined angular momentum along the vertical direction while remaining uncertain along the horizontal directions. Quantum spin follows the same structure. Spin is an intrinsic form of angular momentum carried by particles such as electrons, protons, and neutrons. A particle prepared with a definite spin component along one axis will generally produce uncertain results when its spin is measured along a different axis. This uncertainty is not caused by the particle being too small to examine properly, nor is it simply the result of weak magnets, blurred detectors, or hidden trembling. The different spin components are represented by non-commuting operators. The theory does not permit one quantum state to assign exact values to all of them simultaneously. Matrix mechanics therefore changed more than the method used to calculate atomic spectra. It altered the logical structure of physical quantities. In classical physics, position and momentum are numbers that an object can possess together. In quantum mechanics, they are operators whose order matters. Their relationship places restrictions on the states that can exist and on the distributions of outcomes those states can produce. Uncertainty had acquired a mathematical foundation deeper than ordinary ignorance. The problem was no longer merely that physicists could not discover every value. The structure of the theory suggested that some exact values could not be combined within the same quantum state at all. In 1927, Werner Heisenberg published a paper that attempted to explain what the new quantum mechanics was saying about physical reality. The mathematics of matrix mechanics was already producing successful results, but its meaning remained difficult to picture. Electrons were no longer described through definite classical orbits, and certain physical quantities were represented by mathematical operations whose order could not be exchanged freely. Heisenberg wanted to connect this unfamiliar structure with the practical act of observation. His paper introduced the uncertainty idea in the form that would become famous. The central example involved an imaginary microscope designed to locate an electron using extremely short wavelength light. To see why wavelength matters, consider an ordinary optical microscope. Light passes from an object into a lens, allowing details to be resolved. Smaller details require shorter wavelengths. Visible light can reveal structures down to scales comparable with its wavelength, but it cannot provide a sharply detailed image of something much smaller. An electron is far too small to be located precisely using ordinary visible light. Heisenberg therefore imagined illuminating it with gamma rays, which can possess wavelengths far shorter than those of visible light. A short wavelength would allow the microscope to distinguish a much smaller region of space. The electron's position could therefore be determined with greater precision. But light does not observe an electron from a polite distance. A photon must interact with the electron and scatter from it before entering the microscope. During that interaction, the photon transfers momentum to the electron. The amount and direction of the transferred momentum depend on how the photon is scattered. The microscope's lens can collect photons arriving across a limited range of angles. This range is necessary to form an image, but it means the exact direction in which a particular photon leaves the electron cannot be determined perfectly. Because the outgoing photon's direction is uncertain, the change it produces in the electron's momentum is also uncertain. Using light with a shorter wavelength improves the position measurement, yet a shorter wavelength corresponds to a photon with greater momentum. The collision can therefore produce a larger and less predictable change in the electron's motion. The result is an intuitive trade-off. The more precisely the microscope locates the electron, the less precisely its momentum can be known afterward. Using longer wavelength light would disturb the momentum less severely, but the image would become less precise, and the electron's position would be restricted only to a broader region. It appears that nature prevents both quantities from being determined with unlimited accuracy. Heisenberg's microscope was never intended as a serious proposal for building an especially awkward laboratory instrument. It was a thought experiment, designed to reveal a limitation that could not simply be removed by improving the craftsmanship of the microscope. A better lens might reduce ordinary optical imperfections. A more stable laboratory might eliminate vibrations. A more sensitive detector might register weaker signals. None of these improvements would remove the connection between wavelength, spatial resolution, photon momentum, and recoil. The difficulty appeared to arise from the physical conditions required to perform the measurement at all. This made the microscope a powerful teaching device. It showed that observation in quantum physics cannot always be treated as passive. Measuring devices must interact with the systems they measure, and those interactions can alter the later state of the system. Yet the example also contained a subtle problem. Heisenberg's explanation brought together several different forms of uncertainty. There was the resolution of the microscope, meaning the error or inaccuracy in the position measurement. There was the unpredictable momentum transferred by the scattered photon, meaning the disturbance produced by the measurement. There was also the statistical spread of position and momentum already associated with the quantum state. These quantities are related, but they are not identical. Niels Bohr recognized difficulties in parts of Heisenberg's original reasoning. During discussion surrounding the paper, Bohr argued that the behavior of the microscope had to be analyzed using the wave properties of light, including diffraction through the microscope's aperture. This was more than a technical correction. It reflected Bohr's wider view of quantum phenomena. Bohr developed the principle of complementarity, according to which different experimental arrangements reveal different mutually exclusive aspects of a quantum system. An arrangement designed to reveal precise information about position may prevent the conditions required for a precise determination of momentum. A different arrangement can reveal momentum more sharply, but only by giving up the localization needed for a precise position measurement. The two descriptions are complementary because both are required for a full account of quantum behavior, yet they cannot always be applied together within one experimental arrangement. This does not mean that the electron secretly changes from a perfectly ordinary particle into a wave whenever the laboratory equipment is rearranged. It means that position, momentum, interference, and trajectory information are defined and revealed through different physical conditions. The experiment is therefore not merely uncovering a collection of classical properties that were quietly waiting in the electron all along. Bohr placed strong emphasis on the complete phenomenon, including the system, the apparatus, and the experimental arrangement. He resisted attempts to speak about quantum properties as though they possessed the same independent meaning they had in classical physics. Heisenberg's microscope and Bohr's complementarity are often presented as one simple argument, but their emphases are different. The microscope focuses attention on measurement disturbance. A photon interacts with an electron and changes its momentum. Complementarity focuses on the mutual exclusivity of experimental arrangements and the conditions under which different physical quantities can be meaningfully defined. Later work would separate these ideas more carefully. Preparation uncertainty concerns the spread of possible results already present in a quantum state. Measurement error concerns how accurately an apparatus reports the quantity it is intended to measure. Measurement disturbance concerns how the act of measurement changes another quantity or its later probability distribution. These distinctions matter because the most familiar position and momentum uncertainty relation is not simply a calculation of how hard a photon strikes an electron. It applies to ensembles of identically prepared quantum systems. Position can be measured on one group and momentum on another. The resulting statistical spreads obey the relation, even though no system is subjected to both measurements in succession. No microscope is required. No first measurement needs to disturb a second quantity. The limitation is already present in the mathematical form of the quantum state. This is why Heisenberg's microscope is both illuminating and potentially misleading. It correctly demonstrates that quantum measurements can involve unavoidable physical backaction. It provides a memorable explanation of why increasing spatial resolution can lead to greater momentum disturbance. But it can also encourage the idea that all quantum uncertainty is created by clumsy observation, as though an electron possessed a perfectly exact position and momentum until an energetic photon arrived and spoiled everything. The uncertainty relation makes a deeper statement. Even before a measurement is attempted, a quantum state cannot generally possess arbitrarily narrow position and momentum distributions at the same time. Heisenberg's microscope revealed one important face of quantum uncertainty. The famous mathematical inequality would reveal another. Werner Heisenberg gave quantum uncertainty its famous physical picture, but the inequality most commonly associated with his name was derived more rigorously by someone else. Later in 1927, Earl Hesse Kennard examined the mathematical relationship between position and momentum within wave mechanics. His work produced the precise inequality that now appears in countless physics textbooks as the Heisenberg uncertainty principle. The difference is more than a small historical footnote. Heisenberg's microscope concerned the accuracy of a position measurement and the disturbance that measurement might produce in momentum. Kennard's relation concerned the statistical spreads already contained within a quantum state. These are connected ideas, but they answer different questions. To understand Kennard's result, it helps to begin with standard deviation. Imagine preparing a large number of quantum systems in exactly the same way and measuring the position of each one. The results may not all be identical. Some may cluster near the average position, while others appear farther away. The standard deviation measures how broadly those outcomes are distributed around their average. A small standard deviation means the results are concentrated within a narrow range. A large standard deviation means they are spread more widely. This spread should not automatically be interpreted as an experimental mistake. A measuring instrument might record each individual position with great accuracy, while the collection of accurate results still covers a broad region. In that case, the detector is not failing. The quantum state itself predicts a distribution of positions. The same reasoning applies to momentum. Another collection of identically prepared systems can be measured to determine the momentum distribution and its standard deviation. Kennard showed that these two spreads cannot both become arbitrarily small. The relationship can be stated as the standard deviation of position multiplied by the standard deviation of momentum must be at least 1/2 of the reduced Planck constant. The reduced Planck constant is Planck's constant divided by 2 multiplied by pi. Its value is extremely small in everyday units, which is why the restriction is not obvious for large objects. A tennis ball can be localized to a small region while also possessing a momentum narrow enough for ordinary purposes. The uncertainty relation still applies, but its minimum scale is negligible compared with the size and motion of the ball. For electrons, atoms, photons, and other microscopic systems, the reduced Planck constant establishes a meaningful limit. If the position distribution is made narrower, the momentum distribution must become broader. If the momentum distribution is made extremely narrow, the state must spread more widely across position. The relation does not say that every individual measurement will be inaccurate, nor does it say that one instrument must measure position and momentum simultaneously and return 2 blurred readings. Instead, it concerns the statistical distributions predicted for similarly prepared systems. A laboratory might prepare 10,000 electrons through one carefully controlled procedure. Position could be measured on one portion of the collection, while momentum is measured on another portion prepared in the same state. This use of separate groups matters because a measurement may alter or even absorb the individual system being examined. An electron detected at a screen cannot necessarily be collected afterward and returned to its original state for a second independent measurement. Even when gentler measurements are possible, the preparation uncertainty relation is still defined through the probability distributions associated with the initial quantum state. It does not depend on performing both measurements upon one particle. Kennard's inequality gave the position and momentum relation a firm mathematical foundation. Related treatment soon revealed that the underlying principle was more general. Hermann Weyl examined uncertainty within the broader mathematical structure of quantum theory. In 1929, Howard Percy Robertson developed a relation applying to arbitrary pairs of observables. An observable is a measurable physical quantity represented by a mathematical operator. Position and momentum are observables, but so are energy, angular momentum, and different components of spin. Robertson showed that the uncertainties of 2 observables are connected to their commutator. The result can be stated verbally as the product of the uncertainties in 2 observables is at least 1/2 of the absolute expected value of their commutator. The commutator measures how much the result changes when the order of 2 quantum operations is reversed. When 2 observables do not commute, their operators possess a fundamental order dependence. The expected value is the statistical average predicted for repeated measurements upon identically prepared systems. For position and momentum, the commutator has a fixed value involving the reduced Planck constant. Robertson's general relation therefore reduces to Kennard's familiar position and momentum inequality. For other observables, however, the expected value of the commutator may depend on the particular quantum state. This makes the lower bound state-dependent. 2 non-commuting observables may have a large uncertainty bound in one state and a smaller bound in another. The theory does not assign one identical numerical limit to every pair of observables under every possible condition. Erwin Schrödinger extended Robertson's result further. His treatment included correlations between the 2 observables, producing what is now called the Robertson-Schrödinger uncertainty relation. Correlation describes how deviations in one quantity are connected with deviations in another. Two observables may vary together in a structured way rather than behaving as unrelated spreads. By including this covariance, Schrödinger obtained a stronger and more complete inequality. The additional term captures information that the simpler product of standard deviations may overlook. This refinement matters because the ordinary Robertson lower bound can sometimes become zero. Suppose the expected value of the commutator vanishes for a particular quantum state. Robertson's relation then provides a lower bound of zero for the product of the uncertainties. It may be tempting to conclude that both quantities can therefore be known with unlimited precision. That conclusion would be wrong. A zero lower bound means only that the Robertson inequality, in that particular state, does not provide a useful positive restriction. It does not prove that the two observables commute, share exact values, or can be measured jointly without limitation. The operators may still be incompatible. Higher-order relationships, correlations, or alternative uncertainty relations may reveal restrictions that the basic Robertson expression does not capture. Different spin components provide examples in which the expected commutator can vanish for certain states, even though the underlying observables remain non-commuting. The Robertson-Schrödinger relation improves the description by including covariance, but even it belongs to a larger family of uncertainty relations designed for different tasks. Some relations describe preparation uncertainty. Others describe the accuracy of approximate joint measurements. Some quantify measurement disturbance. Others measure uncertainty using information entropy rather than standard deviation. This is why the familiar phrase the Heisenberg uncertainty principle can create confusion. It is often used as though it names one argument, one equation, and one physical meaning. In reality, Heisenberg's microscope, Kennard's inequality, Robertson's generalization, and Schrödinger's extension describe related but distinguishable aspects of quantum theory. The standard position and momentum inequality says something precise about the spreads permitted within a quantum state. It does not automatically tell us how inaccurate a particular apparatus must be. It does not directly calculate how much one measurement physically disturbs another observable, and it does not require anyone to perform a measurement before the uncertainty exists. The limitation belongs to the probability distributions encoded in the state itself. Heisenberg supplied the memorable intuition. Kennard, Robertson, and Schrödinger reveal the deeper mathematical structure beneath it. Position and momentum uncertainty can be understood without imagining a photon striking a particle or a microscope, disturbing what it tries to observe. The same trade-off appears naturally when a quantum system is described as a wave. Begin with the simplest possible wave, a perfectly uniform sinusoidal wave repeating endlessly through space. Every crest is separated from the next by the same distance. This gives the wave one exact wavelength. According to the relationship proposed by Louis de Broglie, wavelength and momentum are directly connected. In spoken form, the equation is the momentum of a particle equals Planck's constant divided by its wavelength. A wave with one perfectly defined wavelength therefore represents one perfectly defined momentum. But there is an immediate difficulty. An ideal sinusoidal wave does not occupy one small region. It stretches without end in every direction. Its pattern looks the same here, a meter away, and 1,000 kilometers beyond that. It has a precisely defined momentum, but no sharply defined position. Nothing within the wave marks one location as the place where the particle must be found. The state is spread across all of space. To create a wave that is localized, many waves must be combined. Imagine adding several sinusoidal waves with slightly different wavelengths. Their crests can be arranged to line up within one limited region. There, the waves reinforce one another and produce a larger combined amplitude. Away from that region, the crests and troughs no longer align. One wave rises while another falls, causing them to cancel. The result is a concentrated group of waves known as a wave packet. A wave packet can be centered around a particular position. Unlike the endless single wavelength wave, it possesses a recognizable location. Yet localization comes at a cost. Because the packet was created from many different wavelengths, it also contains many different momenta. The narrower the packet becomes in position, the wider the range of wavelengths required to construct it. This produces a broader momentum distribution. If the momentum distribution is narrowed instead, the available wavelengths become more similar. They then take a longer distance to cancel outside the central region, causing the packet to spread more widely through space. Position and momentum are therefore linked by the structure of waves themselves. A narrow position distribution requires a broad momentum distribution. A narrow momentum distribution requires an extended position distribution. This relationship is described mathematically using the Fourier transform. Joseph Fourier developed methods for representing complicated patterns as combinations of simpler sinusoidal waves. A complex wave can be broken into its component frequencies, while a collection of frequencies can be combined to reconstruct the original wave. In quantum mechanics, the Fourier transform connects two descriptions of the same state. One describes how the wave function is distributed through position space. The other describes how it is distributed through momentum space. These are not two unrelated waves. They are two mathematical views of one quantum state. A sharply concentrated position wave function transforms into a broad momentum wave function. A narrow momentum wave function transforms into a widely distributed position wave function. Similar trade-offs appear throughout ordinary wave physics. A pure musical note maintained indefinitely can have one sharply defined frequency. A short burst of sound, however, cannot be built from only one exact frequency. It requires a band of frequencies combined together. The briefer the sound pulse becomes, the wider that frequency range must be. A single, sustained note from a tuning fork is narrow in frequency but extended in time. A quick tap or clap is localized in time but contains a much broader mixture of frequencies. Radio signals, optical pulses and vibrations in strings obey related mathematical limits. Fourier analysis connects the concentration of a signal in one description with its spread in another. These classical examples help explain the mathematics, but they do not settle the meaning of quantum uncertainty. A classical sound wave represents changes in air pressure. A water wave represents the motion of water. Those waves are physical disturbances spread through material or through a field. The quantum wave function plays a more unusual role. Max Born proposed that the squared magnitude of the wave function determines the probability density for measurement outcomes. A large value of the squared magnitude at one location means that a position measurement is more likely to find the particle there. A small value means the result is less likely. The wave function is therefore not merely a blurred photograph of a particle whose exact location is hidden somewhere inside it. It provides the amplitudes from which quantum probabilities are calculated. When position is measured repeatedly on identically prepared systems, the results follow the distribution predicted by the position wave function. When momentum is measured on a separate collection prepared in the same state, the results follow the corresponding momentum distribution. The Fourier relationship between those two descriptions ensures that both distributions cannot be made arbitrarily narrow. Some wave packets achieve the smallest possible product of position and momentum standard deviations. These are called minimum uncertainty states. The most familiar examples have a Gaussian shape, resembling a smooth bell curve. A Gaussian wave packet is concentrated around an average position while fading gradually on either side. Its momentum distribution is also Gaussian. For an appropriately prepared state, the two spreads reach the minimum allowed by the position and momentum uncertainty relation. This does not mean that both quantities become perfectly precise. It means their combined uncertainty is as small as quantum mechanics permits. The same trade-off can be observed through diffraction. Suppose particles travel towards a barrier containing a narrow slit. Passing through the opening confines their transverse position to a limited region. The narrower the slit becomes, the more accurately the particles are localized across that direction. After passing through, however, the particles spread over a wider range of angles. This widening corresponds to a broader range of transverse momenta. A wide slit provides weaker localization and produces less diffraction. A narrow slit provides stronger localization and produces greater diffraction. This behavior has been observed not only with light and electrons, but with atoms, neutrons, and complex molecules. Olaf Nyers, Marcus Arndt, and Anton Zeilinger demonstrated the position and momentum trade-off using fullerene molecules containing 70 carbon atoms. These large cage-shaped molecules were heated to temperatures near 900 Kelvin and sent through narrow openings. Despite their complexity and internal thermal motion, the molecular beam displayed the predicted relationship between spatial confinement and momentum spread. A molecule containing 70 atoms is far larger than an electron, yet it still obeys the same quantum structure. The experiment does not require the idea that an observer creates uncertainty simply by looking. Passing through the slit prepares the molecule within a narrower range of positions. The resulting quantum state necessarily contains a broader range of transverse momenta. The uncertainty is written into the wave packet. A single wavelength can provide exact momentum only by extending without limit. A localized state can occupy a limited region only by containing many momenta. Position and momentum uncertainty are therefore not an arbitrary prohibition added to quantum mechanics. They are woven into the way localization itself is built from waves. A quantum state can be uncertain before any measuring device touches it. This form of uncertainty is known as preparation uncertainty. It describes a restriction on the probability distributions associated with systems prepared in a particular quantum state. The word preparation is important. It refers to everything the laboratory does before the final measurement takes place. A source might produce electrons with a carefully controlled range of energies. Magnetic fields may align the spin of atoms. Lasers can cool particles and place them into selected quantum states. Filters, slits, traps, and electromagnetic pulses can all help create a repeatable preparation procedure. Suppose a laboratory uses the same procedure to prepare many thousands of electrons. The aim is not to manufacture one electron and measure it repeatedly forever. Quantum measurements may change the state, absorb the particle, or leave it unsuitable for another independent test. Instead, the preparation is repeated. One group of electrons is sent towards an apparatus that measures position. Another group, prepared through the same procedure, is directed towards an apparatus that measures momentum. The position measurements produce a distribution of outcomes. The momentum measurements produce another distribution. The standard deviation of each distribution describes how widely the results are spread around their average. Those spreads must obey the position and momentum uncertainty relation. No attempt has been made to measure position and momentum successively on the same electron. There is no first measurement physically disturbing a second one. Each electron encounters only the apparatus chosen for its group. The limitation is already present in the statistical predictions of the prepared quantum state. This distinguishes preparation uncertainty from measurement disturbance. It also separates preparation uncertainty from ordinary measurement error. Imagine that a detector measures the position of an electron to extremely high accuracy. Each reading may be reliable to within a tiny fraction of a meter, yet after thousands of trials the accurate readings may still appear across a broad region. The detector has not performed badly. It has precisely recorded a wide distribution predicted by the state. An imprecise apparatus creates uncertainty because its readings fail to track the intended quantity accurately. A broadly distributed quantum state produces varied results, even when each individual reading is precise. These two situations can look similar if only the final list of numbers is examined. Both may produce a spread of values. Their physical origins, however, are very different. One spread belongs to the limitations of the measuring device. The other belongs to the probability distribution associated with the preparation. A sharply prepared momentum state makes the distinction especially clear. Suppose a source creates particles with momenta concentrated within an extremely narrow range. Repeated momentum measurements may then return nearly identical results. Each detector reading can be precise, and the collection of results can also possess a very small standard deviation. The momentum is sharply prepared. The corresponding position wavefunction, however, must be widely extended. If position is measured on another collection of systems prepared in the same state, the outcomes can appear across a large region. Nothing has gone wrong with the position detector. Its readings may be individually accurate. The broad distribution follows from the structure of the state. In the ideal mathematical limit, a state with one exact momentum is represented by a wave extending throughout all space. Its position is completely delocalized. Real laboratory states are never perfectly infinite, but the trade-off remains. The more tightly momentum is concentrated, the more widely position must generally spread. The reverse is equally important. A state confined to a very small region of space requires a broad range of momentum components. Precise localization is not a free gift. It changes the kind of quantum state that has been prepared. Preparation uncertainty is sometimes called intrinsic uncertainty or state uncertainty. Different researchers and textbooks use these terms in slightly different ways, and their meanings can overlap. All of them point towards the same central idea. A quantum state may predict a genuine statistical spread before the practical imperfections of a measuring instrument are considered. The word intrinsic must still be handled carefully. It can mean that the spread is intrinsic to the quantum state as represented by the formalism. That is a mathematical statement. It does not automatically settle what exists beneath or beyond the formalism. Different interpretations of quantum mechanics tell different stories about the same distributions. In a standard collapse-based account, the state may represent several possible outcomes without one definite value being selected before measurement. In a hidden variable theory, some properties may possess definite values not fully represented by the ordinary wave function. The statistical spread may then reflect incomplete knowledge of those deeper variables. In the many worlds interpretation associated with Hugh Everett the Third, the wave function evolves into branches containing different outcomes. Uncertainty becomes connected to which future branch an observer will experience. In relational quantum mechanics, associated with Carlo Rovelli, properties become definite relative to particular interactions rather than existing as one absolute collection of values for every observer. The same preparation-uncertainty relation can survive within all these pictures. The interpretations disagree about what the distribution represents, not necessarily about which distribution the experiment will reveal. Quantum uncertainty therefore does not mean that physicists know nothing. Quite the opposite can be true. A probability distribution can be known with extraordinary precision. Researchers may calculate its shape, average value, standard deviation, correlations, and evolution over time. Repeating an experiment millions of times can confirm those predictions to impressive accuracy. What remains unpredictable may be the individual result. A fair coin provides a simple classical comparison. Knowing that heads and tails are equally likely does not reveal the outcome of the next toss. Yet quantum probability differs because it cannot generally be treated as ordinary ignorance about a complete collection of local pre-existing values. The wave function is the mathematical object most commonly used to describe a pure quantum state. It assigns complex amplitudes to possible measurement outcomes. The squared magnitudes of those amplitudes determine probabilities. More general situations are described using a density operator. This can represent pure states, statistical mixtures, and parts of larger entangled systems. The density operator may sound like something used to check whether a quantum particle has been eating properly, but its purpose is more formal. It contains the information needed to calculate the probabilities and statistical averages associated with measurements. Both the wave function and the density operator encode preparation uncertainty. They specify the distributions expected for different observables before any final measurement is performed. Separating this state-based spread from measurement disturbance is essential. An experiment testing preparation uncertainty asks whether the distributions produced by a prepared state obey a particular relation. An experiment testing measurement error asks how closely an apparatus reproduces the intended observable. An experiment testing disturbance asks how much one measurement changes the statistics of another observable. These are different questions. They require different definitions, experimental arrangements, and mathematical relations. Without keeping them separate, almost any result can be described vaguely as uncertainty, and the meaning becomes blurred before the detector has even been switched on. Preparation. Uncertainty is the quietest form of the principle. It requires no dramatic collision, and no observer forcing nature to make a decision. The state is prepared. Different measurements are performed on different members of the collection. The distributions appear, and before anyone attempts to measure two incompatible quantities together, the quantum limits are already there. Quantum spin is one of those scientific terms that sounds reassuringly familiar until it is examined closely. The word spin suggests a small object rotating around its own axis, like a planet turning through space or a toy top circling on a table. Quantum particles do possess a form of angular momentum called spin, but they are not tiny solid spheres physically rotating in the ordinary classical sense. An electron cannot be pictured safely as a miniature ball with a little surface whirling around. If its measured spin were produced by literal rotation, parts of that imagined surface would need to move in physically impossible ways. The classical picture simply does not fit. Spin is instead an intrinsic quantum property. It belongs to the particle itself, alongside properties such as mass and electric charge. It behaves mathematically like angular momentum and produces measurable magnetic effects, but it has no exact everyday mechanical equivalent. This makes spin especially useful for understanding uncertainty. Position and momentum can tempt us to blame every limitation on particles being small, fast, or difficult to observe. Spin strips away much of that distraction. It reveals uncertainty through a compact set of clearly separated outcomes. One of the first important clues appeared in 1922 through an experiment designed by Otto Stern and carried out with Walter Gerlach. The Stern-Gerlach experiment sent a beam of electrically neutral silver atoms through a non-uniform magnetic field. Each silver atom possessed a magnetic response connected to the angular momentum of its outer electron. If the atoms had behaved like tiny classical magnets pointing in random directions, the magnetic field should have deflected them by a continuous range of amounts. Some would bend strongly upward, some weakly upward, some barely at all, and others downward across a smooth spread. That is not what appeared. The beam separated into two distinct components. One group of atoms was deflected in one direction, while the other was deflected in the opposite direction. Instead of every possible intermediate value, the measurement produced two discrete results. The original interpretation of the experiment developed before the modern theory of electron spin was complete, but the result later became a classic demonstration of quantist spin components. A Stern-Gerlach apparatus does more than measure spin. It can also prepare a quantum state. Suppose a beam enters an apparatus arranged to measure spin along the vertical direction. The beam divides into an upward result and a downward result. A physical barrier can block the downward branch while allowing only the upward branch to continue. The remaining atoms are now prepared with a definite upward spin component along the vertical axis. If they pass through a second apparatus aligned in the same vertical direction, every atom produces the upward result again. The state is sharp with respect to that particular spin component. Now rotate the second apparatus so that it measures spin along a horizontal direction. The previously prepared atoms no longer produce one certain result. Roughly half are found in one horizontal spin state, while the other half are found in the opposite horizontal state. The vertical spin component was definite. The horizontal spin component was uncertain. This does not mean the first apparatus was poorly adjusted, nor does it mean the second apparatus had weak magnets or unreliable detectors. Repeating the experiment many times produces the same probability pattern with increasing statistical precision. The uncertainty is associated with the prepared state, relative to the new measurement direction. No gamma-ray microscope is required. No energetic photon needs to collide with the atom before the initial horizontal uncertainty exists. Once the state has been prepared with a definite vertical spin component, quantum mechanics already predicts a distribution of possible results for a horizontal spin measurement. The measurement interaction is still physical and can change the state. After a horizontal measurement, the particle becomes associated with the horizontal result that was obtained. But the uncertainty of that result was present in the statistical predictions before the measurement occurred. Wolfgang Pauli helped provide the mathematical description needed to represent spin. The quantities commonly called the Pauli matrices describe spin components along different spatial directions for particles such as electrons. These spin components are non-commuting observables. The operation representing vertical spin does not combine with the operation representing horizontal spin in the same way when their order is reversed. This mathematical order dependence places restrictions on the states that can possess sharply defined values for both. A state with a definite vertical spin component is not also a state with one definite horizontal component. The theory supplies probabilities instead. It may be tempting to imagine that the particle carries a hidden classical arrow pointing in some unknown direction. The measurement would then merely reveal how much of that arrow points along the chosen axis. That picture cannot reproduce the full structure of quantum spin. A classical arrow possesses definite components along all directions at once. Even when those components are unknown, they still exist within the classical description. Quantum mechanics does not generally assign simultaneous sharp values to different spin components. The issue is therefore not merely that the arrow is hidden. Experiments involving sequences of spin measurements show why. Prepare a particle as vertically upward, measure it horizontally, then measure it vertically again. The horizontal measurement produces one of two results, but afterward, the final vertical measurement is no longer guaranteed to return the original upward value. It again produces probabilistic outcomes. The intermediate measurement has changed the state in a way that cannot be understood as simply uncovering an unchanged collection of pre-existing classical components. This does not mean that every interpretation agrees that properties are created from nothing during measurement. Hidden variable approaches can supply deeper descriptions, although they must abandon important features of ordinary local classical physics. The point is narrower and more secure. Spin statistics cannot be reproduced by treating the particle as a simple classical arrow, whose direction is merely unknown. The probabilities themselves are sharply defined. For a particle prepared vertically upward, measurements along a perpendicular axis produce equal probabilities for the two possible outcomes. Measurements along axes tilted by other angles produce different probabilities determined by the geometry of quantum states. The results are not an uncontrolled blur. The apparatus does not return vaguely upward, perhaps sideways or slightly confused. It returns discrete outcomes with precise statistical frequencies. Spin therefore reveals what quantum uncertainty is really concerned with. It is not only a problem of locating a tiny object or tracking its motion. It concerns the compatibility of different physical questions. A preparation that makes one question answerable with certainty can make another question fundamentally probabilistic. This clarity is one reason spin systems are so valuable in modern experiments. Neutron spin can be manipulated using magnetic fields and measured through carefully designed analyzers. Photon polarization provides a closely related two-outcome system that can be prepared, rotated, and detected with high precision. Researchers often use these systems to test measurement error, disturbance, complementarity, entanglement, and alternative forms of uncertainty relations. They offer cleaner experimental control than attempts to follow the exact position and momentum of one microscopic particle. Spin removes the comforting image of an object travelling along a hidden classical path. What remains is the deeper structure of quantum mechanics. One component can be definite, another can be uncertain. The probabilities are exact, even when the individual outcome is not. The particle is not simply spinning in a direction we have failed to discover. The possible questions themselves do not all fit together in the classical way. Energy and time are often introduced as another uncertain pair, placed neatly beside position and momentum. The usual statement says that the uncertainty in energy multiplied by the uncertainty in time cannot fall below a limit set by the reduced Planck constant. It sounds familiar, and in some contexts it is useful. Yet energy and time do not generally enter quantum mechanics in the same way as position and momentum. That difference matters. Position is represented by a quantum observable. Momentum is also represented by a quantum observable. Each has an operator that acts upon the quantum state, and the two operators do not commute. Their uncertainty relation can therefore be derived from the mathematical relationship between those operators. Time usually plays a different role. In ordinary quantum mechanics, time is treated as a parameter. It tells us when a state is being described and how that state evolves. It resembles the time displayed by a clock outside the system, rather than a physical quantity represented by one universal operator inside it. There are specialized approaches in which time observables can be defined for particular situations. Arrival times, durations, and clock readings can all be treated carefully within quantum theory. But there is no single universal time operator that stands beside the Hamiltonian, the operator representing energy, in exactly the same way that position stands beside momentum. For this reason, the phrase energy and time uncertainty relation refers to several different results rather than one universal statement. One important form was developed by Leonid Mandelstam and Igor Tamm in 1945. Their relation connects the energy spread of a quantum state with the characteristic time over which some measurable property of that state changes appreciably. The energy uncertainty is the standard deviation of energy within the state. The time quantity is not simply the uncertainty of a clock reading. Instead, it is constructed from the rate at which the expected value of another observable changes. In spoken form, the central idea is, a state with a small spread in energy generally requires a longer time for an observable to change by an amount comparable with its uncertainty. A state containing only one exact energy is known as an energy eigenstate. Its overall wave function changes with time through a phase, but the probabilities of ordinary time-independent measurements remain constant. Such a state is stationary in the quantum mechanical sense. It does not mean that every internal classical picture is frozen solid. It means that measurable probability distributions do not change with time. A state made from a range of different energies can behave differently. Each energy component evolves at its own rate. Their relative phases change, allowing interference between the components to alter the probabilities associated with measurements. A broader range of energies can therefore support more rapid evolution. This resembles the relationship between frequency range and the duration of a signal. A perfectly pure frequency continues indefinitely, while a sharply localized pulse requires many frequencies. In quantum mechanics, energy is connected to frequency, so a state that changes rapidly often requires a broader energy distribution. The Mandelstam-Tamm relation gives this idea a precise form, but it does not say that time itself is fuzzy in exactly the same manner as position. Another energy and time relationship appears in unstable quantum states. An excited atom, an unstable particle, or a short-lived nuclear state does not remain intact forever. It decays after some characteristic lifetime. Repeating the preparation many times produces a statistical distribution of decay times. The energy associated with the unstable state also has a finite width. A very short-lived state generally produces a broader energy distribution, while a long-lived state can possess a much narrower energy width. This is known as the lifetime width relation. The effect appears in spectroscopy as natural line broadening. An atomic state with a finite lifetime emits radiation across a small range of energies rather than at one infinitely sharp value. This does not mean that energy briefly becomes undefined because nature has misplaced it, nor does it mean that conservation of energy may be ignored while the event is happening. A common popular explanation claims that quantum mechanics allows energy to be borrowed from the universe for a short time, provided that it is returned quickly enough. That description is misleading. Energy conservation remains a central feature of quantum theory. When the laws governing a closed system do not change with time, the total energy is conserved. This connection follows from time translation symmetry and is expressed formally through Emi-Noether's theorem. The lifetime width relation describes the energy distribution of an unstable state. It does not grant temporary permission for physical processes to violate conservation laws. Similar confusion often appears in discussions of virtual particles. Internal mathematical contributions in quantum field calculations are sometimes described as particles borrowing energy for a short interval. That language may offer a rough visual metaphor, but virtual particles are not ordinary detectable particles secretly avoiding conservation laws between measurements. Energy is conserved at the interactions described by the theory. The interpretation of measurement duration created another important debate. Yakir Aharonov and David Bohm analyzed the measurement of energy and challenged the idea that measuring energy with high precision must always require a universally fixed minimum duration. They showed that the relationship between measurement time and energy accuracy depends on the physical measurement procedure. Under suitable conditions, an energy measurement can be completed within a short interval without obeying a simple universal rule in which better accuracy always demands proportionally more time. They also argued that the amount of energy transferred to a system during measurement is not determined by one universal product involving the measurement duration. This did not abolish energy and time uncertainty. It showed that several ideas had again been combined beneath one informal phrase. The spread of energy within a state is one quantity. The time required for that state to evolve noticeably is another. The lifetime of an unstable state is a different kind of duration. The operating time of a measuring device is different again. So is the error with which that device estimates energy. Each can appear in a valid quantum relation, but the relations do not all make the same physical claim. Some energy and time bounds describe how quickly a quantum state can evolve. These are often called quantum speed limits. Others describe the relationship between the lifetime and spectral width of unstable states. Some concern the accuracy and duration of particular measurement procedures. Still others involve specialized time observables defined for specific experimental tasks. Using the same word, time, for all these quantities can create the illusion that they are interchangeable. They are not. The energy and time example therefore reveals something important about quantum uncertainty as a whole. There is no single sentence called the uncertainty principle that can be carried unchanged into every problem. There is a family of mathematical relations, each built from carefully defined quantities and designed to answer a particular question. When those definitions are stated clearly, the apparent contradictions usually become manageable. When they are blended together, energy begins borrowing itself from nowhere, time becomes mysteriously blurred, and the uncertainty principle is asked to explain far more than any one equation actually says. Werner Heisenberg's original picture of uncertainty was built around a simple and compelling idea. To measure a quantum system, an apparatus must interact with it. That interaction may reveal one property while altering another. A more precise measurement of position, for example, may produce a larger and less predictable change in momentum. The intuition is powerful, but it contains two quantities that must be distinguished carefully. The first is measurement error. Measurement error describes the difference between the quantity an apparatus is intended to measure and the result the apparatus actually reports. If a device is meant to determine position, its error reflects how closely the reported position corresponds to the ideal position measurement. An ordinary ruler provides a simple classical comparison. If the smallest marking is 1 millimeter, it cannot reliably distinguish lengths separated by a tiny fraction of that distance. The ruler has limited resolution. Quantum measuring devices also have finite accuracy, although defining that accuracy becomes more subtle when the ideal quantity and the approximate reading cannot both be compared directly on the same individual system. The second quantity is disturbance. Disturbance describes the change produced in another observable by the interaction between the apparatus and the quantum system. Suppose an instrument measures position. The interaction may alter the system's momentum. Disturbance concerns the difference between the momentum before the measurement and the momentum after it, or more generally, the change in the probabilities associated with a later momentum measurement. Error and disturbance are therefore different. Error asks how well the apparatus measures the intended observable. Disturbance asks how much the measurement changes another observable. Neither should be confused with the statistical spread already present in the quantum state. A state may possess a broad position distribution even when every individual position measurement is highly accurate. That is preparation uncertainty. An apparatus may return readings that differ from the ideal position values. That is measurement error. The same apparatus may alter the momentum distribution. That is disturbance. All three are sometimes described casually as uncertainty, but placing them beneath one word does not make them mathematically interchangeable. The distinction becomes especially important in approximate joint measurement. Two incompatible observables, such as position and momentum, cannot generally be measured together with unlimited precision. A laboratory may still design an apparatus that gathers partial information about both. The position estimate may be slightly blurred. The momentum estimate may also be imperfect. By accepting limited accuracy in each result, the apparatus can provide an approximate joint measurement. The central question is then how the two errors are related. Making one estimate more accurate may force the other to become less accurate. The resulting trade-off concerns the performance of a joint measuring procedure, not merely the statistical spread of the initial state. A different arrangement is known as successive measurement. Here, one observable is measured first. A second observable is measured afterward, and researchers examine how the first interaction affected the later result. A precise position measurement may leave the state strongly localized. Because a localized quantum state contains a broad range of momenta, a later momentum measurement may produce a much wider distribution than it would have produced before the position measurement. The first reading can be extremely accurate while still causing substantial disturbance. Accuracy in one observable does not guarantee gentleness toward an incompatible one. Spin provides a clean illustration. A particle can be prepared with a definite vertical spin component. If the vertical component is measured accurately, the state remains compatible with that result. But if the horizontal spin component is measured instead, the state is changed into one associated with the horizontal outcome. A later vertical measurement is then no longer guaranteed to reproduce the original value. The horizontal measurement has disturbed the statistics of the vertical observable. This disturbance is not necessarily a vague physical jolt. It may be a precisely defined change in the state and in the probabilities predicted for later measurements. That leads to another complication. Disturbance can be defined in several mathematically reasonable ways. One definition may compare the value of an observable before and after measurement. Another may compare the full probability distributions. A third may ask how much the first measurement reduces the accuracy of a later measuring device. These definitions need not assign the same numerical amount of disturbance to every experiment. Measurement error faces a similar difficulty. In classical physics, one might compare the true value directly with the reported value. In quantum mechanics, the ideal observable and the approximate measurement may be incompatible. Attempting to determine both on the same system can alter the very quantities being compared. The ideal value may not even exist as one definite pre-measurement number within the chosen interpretation. Physicists must therefore define error operationally. They may compare statistical distributions, operator differences, calibration performance, or the behavior of an apparatus across a range of input states. Each method captures a slightly different meaning of measurement accuracy. This is why one universal numerical definition is difficult to construct. A measure that works well for one experimental task may behave strangely in another. It may report zero error for a specially chosen state, even though the apparatus performs poorly on most other states. The mathematics is not being fussy merely for entertainment. It is trying to state exactly which question the experiment is answering. Weak measurement provides another way to explore these issues. A weak measurement couples the apparatus only gently to each individual quantum system. The information obtained from one trial is extremely limited and may be overwhelmed by noise. The advantage is that the disturbance to each system can be comparatively small. By repeating the procedure across a large ensemble of identically prepared systems, researchers can recover useful statistical information. The individual readings reveal very little, but the average pattern across many trials can estimate properties of the initial state and help characterize the effect of a later, stronger measurement. Weak measurements have been used in modern tests of error and disturbance relations, especially in systems involving photon polarization and spin. They do not allow physicists to read every quantum property secretly without consequences. The limited information gathered in each trial is part of the trade-off. A whisper from one system becomes meaningful only after many systems have whispered together. The deeper problem was already present in Heisenberg's microscope. The thought experiment suggested that position error and momentum disturbance should obey a simple product relation. Greater accuracy in position appeared to require greater disturbance in momentum, yet Heisenberg did not provide one universally applicable definition of error or disturbance. His argument was physically persuasive, but the quantities were not specified with enough precision to establish a general theorem for every quantum measurement. Later researchers therefore had to ask what kind of error was intended, what kind of disturbance was being measured, and whether the proposed product remained valid under those definitions. The answers turned out to depend on how the terms were formalized. That did not make Heisenberg's intuition useless. It made it the beginning of a more careful question. Quantum measurement involves genuine trade-offs, but those trade-offs cannot be understood until statistical spread, measurement error, and physical disturbance are separated. The principle becomes less tidy when the words are defined precisely. It also becomes far more meaningful. Werner Heisenberg's original microscope suggested a simple and memorable rule. The more accurately position is measured, the more strongly momentum must be disturbed. For decades, this idea was often expressed as though measurement error multiplied by measurement disturbance must always remain above a fixed quantum limit. The picture was persuasive. The mathematics, however, was not yet universal. In 2003, Masanao Ozawa published a new error disturbance relation designed to apply to a much wider class of quantum measurements. His results showed that the simple product suggested by Heisenberg's microscope could fall below its traditional lower bound. That statement sounds dramatic, but it must be interpreted carefully. Ozawa did not show that quantum uncertainty had disappeared. He did not prove that position and momentum could both be prepared with unlimited precision. He did not overturn the standard uncertainty relation associated with Earl Hesse Kennard and later generalized by Howard Percy Robertson. Instead, he showed that preparation uncertainty and measurement disturbance obey different mathematical relations. Kennard's relation concerns the standard deviations already present in a quantum state. If a collection of identically prepared systems has a narrow position distribution, its momentum distribution must be broader. That restriction remains intact. Ozawa examined a different problem. He asked how accurately one observable can be measured and how much that measurement changes another observable. His relation contains the measurement error, the measurement disturbance, and two additional terms involving the initial standard deviations of the observables. Written fully in words, its central structure is the measurement error multiplied by the disturbance, plus the measurement error multiplied by the initial uncertainty of the disturbed observable, plus the initial uncertainty of the measured observable multiplied by the disturbance, must remain at least as large as 1/2 of the absolute expected value of the commutator. The additional terms are crucial. They allow the direct product of error and disturbance to become smaller than the traditional heuristic limit. Yet the complete expression still obeys a quantum restriction. A measurement may therefore have a small error and cause a relatively small disturbance in a particular state, without making every form of uncertainty vanish. The initial spreads already present in the state contribute to the full balance. This distinction moved the argument from thought experiments into modern laboratories. One important test used neutron spin rather than the position and momentum of a free particle. Neutron spin provides a controllable quantum system with two possible outcomes along a chosen direction. The experiment was conducted by Jacqueline Earhart, Stefan Sponar, Georg Suliok, Gerald Badurek, Masanao Ozawa, and Yuji Hasegawa. They prepared neutrons in carefully selected spin states and performed successive spin measurements. The first apparatus made an approximate measurement of one spin component. A later apparatus measured another, incompatible spin component. By adjusting the orientation and strength of the first measurement, the researchers could vary both its accuracy and the disturbance it produced. The results did not support a universal rule in which error multiplied by disturbance must always remain above the simple Heisenberg style bound. Under certain settings, the product became smaller. The measurements remained consistent with Ozawa's more general relation, because the additional terms involving the state's original spin uncertainties completed the inequality. A separate experiment at the University of Toronto examined a related question using photon polarization. Lee Razima, Ardhavan Darabi, Dylan Mahler, Alex Hayat, Yasaman Sudagar, and Ephraim Steinberg used weak measurements to estimate the polarization properties of photons before a stronger measurement disturbed them. A weak measurement interacts only gently with each photon. It provides very little reliable information in one trial, but repeated measurements across a large collection reveal a meaningful statistical pattern. This allowed the researchers to compare the initial polarization behavior with the results produced after the stronger measurement. Again, the simple product of measurement error and disturbance could fall below the traditional bound. The data agreed with more general relations that included additional contributions from the initial quantum state. These experiments were sometimes described as violations of the Heisenberg uncertainty principle. That wording can easily mislead. They did not violate Kennard's preparation uncertainty relation. They did not demonstrate simultaneous perfect knowledge of incompatible observables. They tested one particular mathematical interpretation of Heisenberg's error disturbance intuition. The result was not that Heisenberg had been entirely wrong. It was that his verbal picture did not automatically produce one universally valid product formula. Even this did not end the debate. Paul Busch, Pekka Lahti and Reinhard Werner developed an alternative approach to measurement error and disturbance. They argued that a strong Heisenberg-type trade-off can still be defended when error is defined through the overall performance of the measuring apparatus. Their concern involved the difference between state-dependent and device-based definitions. A state-dependent measure asks how accurately an apparatus performs for one particular input state. This can produce surprisingly small errors. An apparatus may give the correct answer for a specially chosen state, even if it performs badly on almost every other state. Imagine a broken clock that happens to display the correct time at one particular moment. Judged only at that instant, its error is 0. Judged as a clock, its performance is less impressive. A device-based definition asks how well the apparatus measures an observable across a broad range of possible states. It treats measurement error as a property of the instrument, rather than only of one carefully selected combination of instrument and input. Paul Busch, Pekka Lahti, and Reinhard Werner developed operational measures based on comparisons between probability distributions. Their relations assess how far an approximate measurement can deviate from the ideal observable over the states for which the difference matters most. Using these definitions, they derived state-independent trade-offs with a more recognizably Heisenberg-like form. This does not simply contradict Masanao Ozawa. The two approaches ask different questions. Ozawa's state-dependent error can describe what happens when a particular state passes through a particular apparatus. The device-based approach asks whether the apparatus should be regarded as a good approximation to the intended observable, more generally. An instrument can perform almost perfectly for one state while remaining unreliable as a universal measuring device. Both descriptions can be mathematically correct. Disturbance creates similar choices. One definition may compare an observable's value before and after the interaction. Another may compare its full probability distributions. A device-based definition may ask how much the first apparatus damages the accuracy of all possible later measurements. Each captures a real operational concern, but they need not assign the same number to the same experiment. The argument is therefore partly mathematical and partly conceptual. Physicists must decide what they mean by measurement error before calculating it. They must specify what kind of change deserves to be called disturbance. Only then can an uncertainty relation be tested. This is not a weakness unique to quantum physics. Scientific quantities often become sharper as experimental questions become more precise. Quantum measurement simply makes the distinctions impossible to ignore. The modern experiments confirm that the simplest error multiplied by disturbance formula is not universally valid under every definition. They also confirm that broader quantum restrictions remain. No detector quietly escaped quantum mechanics. No neutron achieved perfect incompatible spin values. No photon revealed every polarization property without consequence. What changed was the language used to describe the trade-off. Two physicists may examine the same apparatus, accept the same recorded data, and agree on every observed probability. One may calculate Ozawa's state-dependent error. Another may apply a device-based measure developed by Paul Busch, Pekka Lahti, and Reinhard Werner. Their numerical answers may differ because the quantities have been defined to answer different questions. The disagreement is not necessarily about what the experiment did. It is about which aspect of what it did deserves the name measurement error, and which change deserves the name disturbance. Standard deviation is not the only way to describe uncertainty. It works well when measurement outcomes are arranged along a numerical scale such as position, momentum, or energy. A narrow distribution has a small standard deviation, while a broad distribution has a larger one. But some quantum measurements do not produce results that fit naturally along a continuous scale. Spin may offer only two possible outcomes along a chosen direction. Photon polarization can also be described through discrete alternatives. In these cases, a different language can sometimes express uncertainty more directly. That language comes from information theory. In tropic uncertainty, relations measure how unpredictable a collection of possible outcomes is. Instead of asking how far results spread from an average value, they ask how much information would be needed to specify which result occurred. The word entropy appears in several areas of physics, so it must be handled carefully. Thermodynamic entropy is connected with the number of microscopic arrangements compatible with the large-scale condition of a physical system. It helps describe heat, equilibrium, and the tendency of energy to disperse. Information entropy is related, but it is not identical in every context. It quantifies uncertainty within a probability distribution. If one outcome is certain, the information entropy is low. There is no surprise when the measurement is performed because the result is already predictable. If several outcomes are equally likely, the entropy is higher. More information is required to identify which result appeared. A fair coin provides a simple classical example. Before the toss, heads and tails are equally likely, so the result contains one unit of binary uncertainty. A coin that always lands heads would have no uncertainty at all, although it would also be a deeply disappointing coin. In quantum theory, information entropy can be used to describe the unpredictability of measurement outcomes for incompatible observables. David Deutsch developed an important entropic form of the uncertainty principle during the 1980s. His work shifted attention away from the widths of numerical distributions and towards limits on the combined predictability of different quantum measurements. Hans Maassen and Josu Fink later derived a stronger and widely used entropic uncertainty relation. Their result connects the uncertainty of two measurements with the degree of overlap between their possible states. When the measurement bases are strongly incompatible, a state that makes one measurement highly predictable must make the other comparatively unpredictable. This can remain informative in situations where a variance-based relation becomes weak. The Robertson uncertainty relation depends on the expected value of a commutator. For some states, that expected value can be zero, even when the observables themselves do not commute. The resulting lower bound may then say only that the product of the standard deviations must be greater than or equal to zero. This is mathematically true, but not especially revealing. It is rather like being told that a journey will take at least no time at all. An entropic relation can still provide a meaningful positive restriction because it examines the entire pattern of probabilities rather than only their average spread. The idea becomes especially clear through mutually unbiased measurement bases. Two measurement bases are mutually unbiased when complete certainty in one produces a perfectly even distribution of outcomes in the other. Spin offers a simple example. Suppose an electron is prepared with a definite upward spin component along the vertical direction. A vertical spin measurement then produces the upward result with certainty. The information entropy of that vertical measurement is zero because there is no unpredictability. Now measure spin along a horizontal direction. Quantum mechanics assigns equal probabilities to the two possible horizontal results. The outcome is maximally uncertain for a two-result measurement. Knowing the vertical spin result provides no ability to predict whether the horizontal result will be one way or the other. The vertical and horizontal spin bases are mutually unbiased. The same relationship works in reverse. A particle prepared with a definite horizontal spin component gives completely unpredictable results when measured vertically. The entropic uncertainty relation states that the combined uncertainty of the two measurements cannot fall below a limit determined by their incompatibility. One measurement may be made perfectly predictable, but only at the cost of increasing uncertainty in the other. Alternatively, both may retain intermediate amounts of uncertainty. This formulation answers a practical question very directly. How difficult is it to predict the outcome when one of two incompatible measurements may be performed? The answer can be expressed in terms of information. If the two measurements are highly incompatible, no preparation allows an observer to predict both sets of outcomes with unlimited success. The quantum state cannot function as a complete answer sheet for every possible measurement basis. This idea has important uses in quantum technology. Quantum random number generators use measurements whose outcomes are unpredictable according to quantum theory. A particle may be prepared in a state that gives equal probabilities for two possible results in the chosen measurement basis. Each trial then produces a sequence of outcomes that can be converted into random bits. The aim is not merely to observe a pattern that looks complicated. A deterministic computer can produce sequences that appear irregular while remaining completely fixed by an initial calculation. Quantum random number generation seeks to certify unpredictability from the physical structure of the experiment. Entropic uncertainty relations help establish limits on how much advance information any observer could possess about the outcomes. In more sophisticated systems, additional tests can distinguish genuine quantum randomness from technical noise, detector bias, or hidden correlations within the equipment The same ideas support quantum key distribution. Quantum key distribution allows two parties to create shared secret information using quantum states and incompatible measurement choices. The best-known early proposal was developed by Charles Bennett and Gilles Brassard in 1984. In a simplified version, one participant prepares photons using one of two possible polarization bases. The other measures each photon using a basis chosen independently. When the bases match, their results can contribute to a shared key. When the bases differ, the outcomes are generally unpredictable. An eavesdropper does not know in advance which measurement basis will later be declared relevant. Attempting to measure each photon in one basis gains information about some possible preparations, but loses information about incompatible ones. The eavesdropper may also disturb the quantum states, producing errors that the legitimate participants can detect by comparing part of their data. Entropic uncertainty relations express the information limit behind this security. Greater predictability for one possible measurement basis requires reduced predictability for the incompatible basis. The uncertainty is therefore not merely a philosophical inconvenience. It restricts how information can be acquired, copied, predicted, and communicated. This information-based viewpoint changes the emphasis of the discussion. Instead of asking whether a particle carries precise values for every observable, it asks which outcomes can be predicted and how much information is available to a particular observer. That shift can make uncertainty more operational. Prediction success, probability distributions, and communication security can all be tested without first deciding what the wave function ultimately represents. Yet the philosophical question does not disappear. One interpretation may treat the probability distribution as an objective feature of a physically indeterminate world. Another may regard it as an expression of incomplete knowledge. A third may connect it with branching outcomes, relational facts, or the expectations of an observer. Entropic uncertainty tells physicists how much can be predicted. It does not by itself decide whether the missing information was absent from reality or merely absent from the observer. Entanglement changes the meaning of uncertainty because it changes what counts as the complete physical system. Two quantum systems are entangled when their joint state cannot be separated into one independent state for the first system and another for the second. The systems may be far apart, yet their measurement probabilities remain linked through one shared quantum description. This does not mean that each particle secretly carries a full set of matching answers. The correlations predicted by quantum mechanics are stronger and more structured than ordinary classical instructions can produce. Consider two particles prepared in an entangled spin state. If one particle is measured along a chosen direction, the result may be completely unpredictable. An observer examining only that particle sees equal probabilities for the available outcomes. Yet the combined state can be known precisely. Quantum mechanics may predict that when both particles are measured along the same direction, their results will always be correlated or always opposite depending on the state prepared. Each local result is uncertain. The relationship between them is exact. Imagine that Alice holds one particle while Bob holds the other. Alice plans to measure either vertical spin or horizontal spin. Before she chooses, Bob cannot predict her result using ordinary classical information alone. If Bob measures his entangled particle in the same direction Alice selects, however, his result may allow him to infer hers with certainty or with much greater accuracy than would otherwise be possible. The uncertainty faced by an observer can therefore depend on whether that observer holds a correlated quantum system. In 2010, Mario Berta, Matthias Christandl, Roger Kolbeck, Joseph Renes, and Renato Renner developed an uncertainty relation that includes quantum memory. Their result extended earlier entropic uncertainty relations by accounting for information stored in an entangled system. When an observer has only classical information, two incompatible measurements must retain a certain minimum amount of combined uncertainty. When the observer also possesses an entangled quantum memory correlated with the measured system, that lower bound can be reduced. This does not violate the uncertainty principle. the relation explicitly includes the entanglement and the physical information available to the observer. Suppose Alice and Bob share two spin particles in a maximally entangled state. Alice chooses to measure either the vertical or horizontal spin component. Without access to Bob's particle, each of Alice's possible results appears random. If Bob is told which direction Alice selected, he can measure his particle along the corresponding direction. The entangled correlations then allow him to predict her outcome far more successfully. Bob does not know in advance which result Alice will obtain. His advantage comes from possessing a quantum system whose state is correlated with hers. The uncertainty is therefore relational. It is not always meaningful to describe one amount of uncertainty as though it belongs permanently to one isolated particle. The assigned uncertainty can depend on the measurement considered, the correlations present, and the physical information accessible to the observer making the prediction. This does not make uncertainty merely subjective. The correlations are objective features of the prepared joint state. Different observers gain different predictive abilities because they possess different physical resources. One observer may hold only a classical record. Another may hold an entangled quantum memory. Quantum mechanics assigns different uncertainty bounds to those situations. Entropic uncertainty relations with quantum memory can help detect entanglement. If observed correlations allow an observer to predict incompatible measurements more accurately than any unentangled state would permit, the result provides evidence that the systems share entanglement. The same principles support quantum communication because the joint state contains correlations unavailable to independent classical systems. Quantum cryptography also relies on these limits. A legitimate receiver who holds the correlated quantum system may predict measurement results well, while an eavesdropper without that system remains uncertain. Security still depends on noise, detector behavior, and the precise protocol. Entanglement is not a magical padlock. Yet modern security proofs can use uncertainty relations to place quantitative limits on the information available to an outsider. The contrast between local uncertainty and global certainty is especially revealing. Each particle in an entangled pair may lack a pure quantum state of its own. Its local description can be a mixed state, predicting random outcomes for several measurements. The pair as a whole, however, may occupy one perfectly defined pure entangled state. Nothing is missing from the global quantum description. The uncertainty appears when attention is restricted to one part of the system or to one observer's accessible information. If uncertainty were simply a fixed property carried by an individual particle, entanglement would be difficult to explain. The same local result can be unpredictable to one observer and predictable to another who holds the correlated partner. The relevant structure includes the state, the chosen measurement, the entanglement between systems, and the information physically available to the observer. A distant measurement can reveal what another distant result must be, yet it cannot send a controllable message faster than light. Each local outcome remains random until the observers compare their records through ordinary communication. Even so, the correlations raise an unavoidable philosophical question. When Bob measures his particle and can infer Alice's result, has he discovered a value that already existed, helped define a value relationally, or simply updated his information about a shared quantum state? Entanglement makes uncertainty less like a fog surrounding one isolated object. It becomes part of the relationship between physical systems, possible measurements, and the observers who hold different pieces of the quantum whole. Albert Einstein never doubted that quantum mechanics was extraordinarily successful. He helped create the quantum revolution himself. What troubled him was the suggestion that probability might be the final description of an individual physical system. For Einstein, a complete theory should describe what exists, not merely the chances of what an experiment might reveal. If quantum mechanics assigned several possible outcomes to a particle, he suspected that deeper facts were missing from the wavefunction. This concern reached its most famous form in 1935, when Albert Einstein, Boris Podolsky, and Nathan Rosen published an argument claiming that quantum mechanics might be incomplete. Their reasoning began with a criterion of physical reality. If the value of a physical quantity can be predicted with certainty, without disturbing the system, then there appears to be an element of physical reality corresponding to that quantity. Einstein, Podolsky, and Rosen applied this idea to two entangled systems. They imagined particles prepared so that their positions and momenta were strongly correlated. Suppose the particles move far apart. By measuring the position of the first, an observer can predict the position of the second. Alternatively, by measuring the momentum of the first, the observer can predict the momentum of the second. The second particle is distant, so the measurement performed on the first appears unable to disturb it through any ordinary local interaction. According to their criterion, the second particle should possess an element of reality corresponding to position. It should also possess one corresponding to momentum because either quantity could be predicted through a chosen measurement on the distant partner. Yet standard quantum mechanics did not assign exact values of both position and momentum to that particle simultaneously. Einstein, Podolsky, and Rosen concluded that the wavefunction could not be complete. Deeper variables seemed necessary to account for the definite properties they believed must exist. Niels Bohr replied quickly. Bohr did not accept that the distant system could be discussed independently of the complete experimental arrangement. Choosing to measure position on the first particle establishes one kind of phenomenon. Choosing momentum establishes another. For Bohr, the phrase "without disturbing the system" was too narrow if disturbance meant only a mechanical push through space. Changing the experimental arrangement changed the conditions under which a physical quantity could be meaningfully defined. Bohr therefore rejected the assumption that the unperformed alternative measurement revealed another simultaneously existing classical property. Einstein wanted properties that existed independently of which measurement was chosen. Bohr argued that quantum phenomena could not be separated from the experimental conditions that made particular descriptions possible. For years the argument appeared philosophical. Then John Stewart Bell found a way to bring part of it into the laboratory. In 1964, Bell proved that a broad class of local hidden variable theories must obey statistical limits now called Bell inequalities. A local hidden variable theory assumes that outcomes are determined by properties carried by the particles, and that no influence travels between distant systems faster than light. The particles may share instructions established when they were created, but each result must depend only on the local setting and those pre-existing variables. Quantum mechanics predicts entangled correlations that can violate Bell inequalities. This created an experimental choice. If nature obeyed the inequalities, local hidden variables might explain uncertainty as ordinary ignorance. If nature violated them under controlled conditions, that local classical picture would fail. During the 1970s and 1980s, Alain Aspect, Philippe Grangier, Gérard Roget, and Jean Dalibard carried out increasingly refined tests using entangled photons. The measurement settings were changed while the photons were travelling, reducing the possibility that each side could adjust through an ordinary signal from the other. The observed correlations agreed with quantum mechanics and violated Bell inequalities. Later research groups closed important loopholes involving detector efficiency, particle selection, and the separation of measurement events. Modern Bell tests continue to support the quantum predictions. Quantum probabilities, therefore, cannot generally be understood as ignorance about a complete set of local properties carried independently by each particle. Any deeper theory reproducing the observed correlations must abandon at least one assumption used in deriving Bell inequalities. This does not prove that no hidden variable theory can exist. David Bohm's pilot wave theory gives particles definite positions guided by a wavefunction. It reproduces ordinary quantum predictions, but it is explicitly non-local. The behavior of one part of an entangled system depends upon the wide configuration. Bell tests therefore rule out broad classes of local hidden variable models, not every conceivable deeper ontology. They also do not prove that every property is literally created by observation. A violation of Bell inequalities shows that local pre-existing values cannot explain all quantum correlations under the usual assumptions. It does not select one unique alternative. The results can be understood through non-local hidden variables, branching worlds, objective collapse, relational properties, or other interpretations that reproduce the same tested probabilities. Nor do Bell correlations allow controllable messages to travel faster than light. Each local result remains unpredictable. The correlations appear only when distant records are compared through ordinary communication. Einstein's preferred local classical picture did not survive intact. His demand for conceptual clarity, however, remained productive. The argument he began transformed a question about completeness into one of the most precise experimental programs in modern physics. Experiments now tell us that uncertainty cannot be reduced to simple ignorance about local instructions hidden inside isolated particles. They do not tell us with equal certainty what must replace that picture. Einstein and Bohr would recognize the argument in its modern form. The answers are more tightly constrained, and several comforting possibilities have been removed. Yet the equations and experiments still leave more than one account of what exists behind the observed results. Physics has narrowed the mystery. It has not chosen one universally accepted reality. Quantum mechanics is extraordinarily successful at predicting what laboratories will observe. Its equations describe atomic spectra, semiconductor behavior, lasers, chemical bonds, and particle collisions with remarkable accuracy. The argument begins when physicists ask what those equations are actually describing. An interpretation of quantum mechanics normally preserves the tested predictions, while offering a different account of the wave function, probability, measurement, and physical reality. The same experiment may produce the same numbers under several interpretations, even though each tells a different story about what happened. The Copenhagen family of interpretations is associated with Niels Bohr and Werner Heisenberg, although their views were not identical and should not be compressed into one rigid doctrine. Copenhagen-style approaches generally treat the quantum formalism as a way of assigning probabilities to measurement outcomes. They resist the assumption that every classical property must possess a definite value before the experimental conditions required to define it are present. A particle prepared with a definite vertical spin component does not also need to carry one hidden, equally definite horizontal spin value. The two measurements represent incompatible physical questions. Uncertainty is therefore not merely ignorance about a complete classical state. It reflects a limit on assigning simultaneous classical properties to a quantum system. The measurement problem remains because the wave function can evolve into a superposition of possible results, while an experiment produces one recorded outcome. Copenhagen accounts usually introduce some form of collapse or state update, although physicists disagree about whether this is a physical event or a change in information. Hugh Everett the Third proposed a different picture in 1957. In his relative state formulation, the universal wave function never undergoes a special collapse. It evolves continuously according to the quantum equations. During measurement, the observer, apparatus, and system become entangled. Each possible outcome appears in a different branch of the total wave function. This later became associated with the many worlds interpretation. Uncertainty becomes subtle, because every allowed result occurs within the branching state. Before measurement, an observer may be uncertain about which future branch will contain their experience. Physicists must then explain why branch weights behave like probabilities when all branches remain part of reality. David Bohm's pilot wave theory offers another alternative. In Bohmian mechanics, particles possess definite positions at all times. Their motion is guided by the wave function through a precise law. Apparent randomness arises because observers do not know the exact initial configuration. Position uncertainty is therefore epistemic. Yet Bohmian mechanics does not restore ordinary classical physics. Its guiding dynamics are non-local, especially for entangled systems. Momentum also does not generally exist as a hidden classical momentum independent of the guiding wave. The theory gives special status to position rather than assigning classical values to every observable. Other interpretations change the equations themselves. Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber developed an objective collapse model in which quantum states undergo rare, spontaneous collapses. Microscopic systems usually retain ordinary quantum behavior, while the many particles in macroscopic objects make collapse effectively unavoidable. Roger Penrose later argued that gravity might help trigger genuine reductions of quantum states, although no confirmed theory has established that mechanism. In objective collapse theories, part of quantum randomness is a real physical process. One outcome is selected because the state genuinely changes, not because an observer merely updates information or becomes separated into branches. These models can differ experimentally from standard quantum mechanics. Researchers therefore search for spontaneous radiation, unexplained heating, loss of interference, and other possible signs of collapse. Relational quantum mechanics associated with Carlo Rovelli proposes that physical properties become definite only relative to interactions between systems. A value does not need to exist as one absolute fact from every possible perspective. When one system interacts with another, a definite result can exist relative to that relationship. A different system may describe the situation differently without contradiction. Uncertainty is then relational. It depends on which system is asking the physical question, and which interactions have established definite correlations. Quantum Bayesian approaches move further towards an informational view. Christopher Fuchs, Rudiger Schack, and Carlton Caves helped develop the idea that a quantum state expresses an agent's expectations about the consequences of actions performed upon the world. The probabilities are personal in the technical Bayesian sense. They represent rational degrees of belief constrained by quantum theory. This does not mean the external world is imaginary, nor does it reduce uncertainty to ignorance about ordinary hidden variables. The world can respond unpredictably, while the wave function remains a tool for organizing expectations rather than a material wave. The interpretations can be compared through a few direct questions. What is uncertain before measurement? For Copenhagen-style accounts, certain properties may lack simultaneous classical definition. For many worlds, the observer is uncertain about future experience even though every branch exists. For Bohmian mechanics, particle positions are definite but unknown. For objective collapse theories, possibilities remain until a genuine random collapse selects one. For relational quantum mechanics, values are definite only relative to interactions. For quantum Bayesian approaches, uncertainty belongs to an agent's expectations. What changes during measurement? A Copenhagen account may introduce collapse. Many worlds produces entanglement and branching. Bohmian particles follow definite guided trajectories. Objective collapse theories add a real stochastic event. Relational quantum mechanics establishes a new fact between systems. Quantum Bayesian approaches treat the outcome as an experience that updates probabilities. Does one outcome become uniquely real? Copenhagen approaches usually say yes at the level of recorded experience. Objective collapse theories say yes through a physical process. Bohmian mechanics always contains one actual particle configuration. Many worlds says every branch remains within the wave function. Relational quantum mechanics and quantum Bayesian approaches answer in ways that depend more strongly on relationships and agents. Is the wave function real? Many worlds treats it as part of the basic ontology. Bohmian mechanics gives it a guiding role. Objective collapse theories treat it as physically evolving and collapsing. Copenhagen, relational, and quantum Bayesian approaches are more cautious about treating it as a literal material object. Laboratory agreement, therefore, does not produce agreement about ontology. Some interpretations mainly reinterpret the same formalism and cannot be separated experimentally if they always predict identical results. Others, especially objective collapse theories, modify the dynamics and can in principle be tested. no interpretation has achieved universal acceptance. Quantum uncertainty may represent ignorance, indefiniteness, branching, relational information, agent-dependent expectation, or genuine stochastic collapse. The mathematics tells physicists how probabilities behave. Interpretation asks what those probabilities are probabilities of. The quantum world appears most clearly when a system is protected from everything around it. An isolated electron, atom, photon, or molecule can remain in a coherent superposition, allowing different possible states to interfere with one another. In principle, the same rules apply to larger objects. In practice, however, large objects are never truly alone. The process that explains much of this transition is called environmental decoherence. Heinz-Dieter Zeh developed some of the earliest modern ideas behind decoherence during the 1970s. Wojciech Zurek later expanded the theory and helped show how interactions with the environment can make quantum possibilities behave increasingly like the definite alternatives of classical physics. A quantum system in a laboratory is surrounded by other physical systems. Photons scatter from it. Air molecules collide with it. Thermal radiation carries away information. Measuring devices become correlated with its state. Even the walls of the apparatus contribute countless environmental degrees of freedom. Each interaction can entangle the system with its surroundings. Suppose an object is placed into a superposition of two different positions. One part of the quantum state corresponds to the object being in one location, while another corresponds to it being somewhere else. If the object were perfectly isolated, those components could remain coherent. Their quantum amplitudes might later be recombined, producing an interference pattern that reveals the presence of the superposition. Now allow a single photon to scatter from the object. The photon leaves carrying information about which position it encountered. Another photon does the same. Air molecules collide with the object and become correlated with its location. Before long, information about the alternatives has spread into a vast number of surrounding particles. The two components of the superposition no longer evolve independently of the environment. Each becomes entangled with a different environmental state. The phase relationship between them has not necessarily vanished from the complete quantum description. It has been dispersed into correlations involving the system and an enormous number of environmental degrees of freedom. Recovering those correlations would require controlling every scattered photon, every collision, and every relevant interaction. For a macroscopic object, that task is so far beyond practical possibility that the lost interference may as well have disappeared. Decoherence therefore suppresses observable interference between different components of a superposition. It does not usually destroy the quantum state through one dramatic event. Instead, coherence leaks into the environment with extraordinary speed. The particular states that remain most stable under this process are known as pointer states. Wojciech Zurek introduced this term to describe states that can survive environmental monitoring without immediately becoming spread across many alternatives. They are selected by the type of interaction occurring between the system and its surroundings. Position often becomes the preferred approximately classical variable for macroscopic objects, because environmental interactions are strongly sensitive to location. Photons scatter from where an object is. Air molecules strike its surface at particular positions. Nearby matter responds to its gravitational and electromagnetic presence in space. As a result, superpositions of widely separated positions decohere extremely rapidly, while states reasonably well localized in position remain comparatively stable. The exact decoherence time depends on the size of the object, its temperature, the distance between the alternatives, and the strength of its coupling to the environment. A small molecule traveling through a high vacuum may preserve coherence long enough to produce observable interference. A warm grain of dust in ordinary air would decohere vastly faster. For an everyday object separated into visibly different positions, the estimated decoherence time can be far shorter than a billionth of a second and, under common conditions, many orders of magnitude shorter still. Human perception operates across timescales of roughly hundredths or tenths of a second. Decoherence for a large warm object can therefore occur before any nervous system has the slightest opportunity to notice the superposition. This helps explain why tables, cups, and laboratory instruments appear to occupy definite positions. They are continually monitored by their environments, whether or not a person is present. After decoherence, the local state of the system behaves much like an ordinary statistical mixture. A coherent superposition differs from a classical mixture because its components can interfere. Once environmental entanglement suppresses that interference, measurements performed only on the system produce statistics resembling a collection in which one alternative or another occurred with ordinary probabilities. For most practical purposes, the alternatives can then be treated as separate classical possibilities. But practical resemblance is not the same as a complete solution. Decoherence does not, by itself, select one unique outcome from the total quantum state. The full description still contains the system, apparatus, and environment entangled across different alternatives. It explains why interference becomes inaccessible and why distinct outcomes no longer visibly overlap. It does not automatically explain why one particular result is experienced rather than another. Maximilian Schlosshauer has emphasized this distinction in detailed analyses of decoherence and the measurement problem. Decoherence is essential for understanding the emergence of classical behavior, but its meaning depends partly on the interpretation surrounding it. In the many worlds, interpretation, decoherence separates branches that no longer interfere appreciably. Each branch contains a different recorded outcome. In Copenhagen's style approaches, decoherence helps explain why measurements can be treated as producing effectively classical alternatives, although some additional account of collapse or state updating may still be required. In relational quantum mechanics, environmental interactions establish stable facts relative to particular systems. In objective collapse theories, decoherence occurs alongside a deeper physical mechanism that genuinely selects one outcome. The same environmental process can therefore support several different interpretations without choosing between them. Decoherence also clarifies how stable records emerge. A measuring device becomes entangled with the system, and the environment rapidly spreads copies of the result through photons, heat, and surrounding matter. Once the information has been widely distributed, reversing the process becomes fantastically improbable. The record behaves as though it is permanent and classical. Quantum uncertainty remains beneath this stability. The probabilities have not been replaced by ordinary deterministic mechanics. Instead, environmental interactions prevent the alternative amplitudes from interfering in ways that are locally observable. The everyday world looks definite not because quantum mechanics stops applying, but because quantum systems are constantly becoming entangled with everything around them. Decoherence explains why possibilities fade from view. It does not tell us why one possibility becomes the single reality we experience. Experiments have confirmed quantum uncertainty in many forms, but they have not assigned one universally accepted meaning to it. The clearest demonstrations begin with preparation uncertainty. When particles pass through a narrow opening, their position across that direction becomes more tightly confined. Beyond the slit, the beam spreads over a wider range of angles, revealing a broader distribution of transverse momentum. This diffraction pattern has been observed with photons, electrons, neutrons, atoms, and complex molecules. The narrower the slit, the broader the momentum distribution becomes. The effect is not caused by a detector returning vague readings. It follows from the quantum state prepared by the aperture. Olaf Nyers, Marcus Arndt, and Anton Zeilinger demonstrated the same relationship with fullerene molecules containing 70 carbon atoms. These warm, complex molecules still produce the expected trade-off between localization and momentum spread, showing that uncertainty remains relevant beyond individual atoms. A different experiment explored uncertainty between superconducting phase and particle number. Wim Elion, Marco Matters, Ulrich Geigenmüller, and Hans Muij studied a small superconducting device in which electric current is carried by Cooper pairs, each formed from two correlated electrons. Their experiment examined the relationship between superconducting phase and the number of Cooper pairs on a small island. A more sharply defined particle number was associated with a less definite phase, while strong phase definition required greater uncertainty in number. Other experiments have tested measurement disturbance instead of preparation uncertainty. Jacqueline Earhart, Stefan Sponar, Georg Sulyok, Gerald Bederek, Masanao Ozawa, and Yuji Hasegawa used successive neutron spin measurements to compare measurement error with disturbance to an incompatible spin component. Lee Rozema, Ardavan Darabi, Dylan Mahler, Alex Hyatt, Yasaman Sudagar, and Ephraim Steinberg performed a related photon polarization experiment using weak measurements. Both investigations found that a simple error multiplied by disturbance product could fall below the traditional heuristic bound associated with Werner Heisenberg. The results remained consistent with more general relations containing additional contributions from the initial quantum state. These experiments did not overturn preparation uncertainty. They showed that measurement error, disturbance, and state uncertainty are distinct quantities requiring separate definitions. Entropic uncertainty has also been tested through measurements designed around predictability rather than standard deviation. When a quantum state gives a definite result in one measurement basis, an incompatible basis can produce a broad or uniform distribution. Spin and photon polarization provide especially clean examples. These limits help certify quantum randomness and restrict what an eavesdropper can learn during quantum key distribution. Entanglement adds another layer. Two local outcomes may each appear random while their correlations are predicted precisely. An observer holding one member of an entangled pair may predict the result obtained from the other more accurately after learning which measurement was chosen. Experiments involving quantum memory therefore show that uncertainty depends partly on which physical correlations are available to an observer. Modern quantum technologies do not defeat these limits, they work within them. Quantum sensing often uses squeezed states. Such a state reduces noise in one observable while increasing it in a complementary observable. This can improve sensitivity when only one quantity carries the desired signal. The practical achievement lies not in escaping quantum limits, but in arranging them so that the most useful observable carries less unwanted noise. Atomic clocks use carefully prepared atomic states to compare extremely stable frequencies. Interferometers use phase differences to detect tiny changes in distance, acceleration, rotation, or gravitational field. The laser interferometer, gravitational wave observatory, uses optical measurements whose sensitivity can be limited by quantum fluctuations. Squeezed light reduces noise in the relevant range while complementary uncertainty increases elsewhere, as quantum mechanics requires. Quantum communication exploits entanglement and uncertainty, while random number generators turn unpredictable outcomes into usable sequences. Quantum cryptography converts limits on prediction into security. In every case, uncertainty is redistributed, correlated, or optimized. It is not removed. Several conclusions are now broadly accepted. A single quantum state cannot generally possess arbitrarily narrow probability distributions for incompatible observables. Approximate joint measurements face quantitative trade-offs. Measuring one observable can alter the statistics of another. Entanglement can change the uncertainty faced by observers with access to different information. What remains disputed is the interpretation. Physicists disagree about which definition of measurement error best captures Werner Heisenberg's original intention. They disagree about whether the wavefunction is a physical entity, an informational object, or something whose meaning depends on interpretation. They also disagree about whether individual outcomes are fundamentally random, whether deeper variables exist, and which properties can meaningfully exist before measurement. Future experiments may eliminate particular possibilities. objective collapse theories modify ordinary quantum dynamics and can be constrained through searches for unexplained heating, spontaneous radiation, or loss of interference. Interpretations predicting exactly the same experimental statistics are harder to separate. If two accounts reproduce every observable result, no ordinary experiment can choose between them without additional assumptions or new predictions. The laboratory verdict is firm but limited. Quantum uncertainty is real as a mathematical and experimental structure. Its distributions, correlations, and trade-offs have been confirmed across an extraordinary range of systems. Physicists continue to argue because uncertainty refers to several questions at once. It can describe a spread within a prepared state, an error in a measuring device, a disturbance caused by interaction, a limit on predictability, or an observer's lack of access to quantum correlations. The experiments have established the limits. What those limits reveal about reality remains the uncertain part. Physicists do not seriously dispute that quantum uncertainty exists. The equations predict it, and experiments confirm it across light, electrons, atoms, neutrons, molecules, and superconducting devices. The disagreement concerns the physical story attached to those successful predictions. Classical uncertainty usually meant missing information. A planet, molecule, or rolling ball was assumed to possess definite properties, even when nobody knew them exactly. Max Planck's energy quanta, Albert Einstein's light quanta, and Louis de Broglie's matter waves began to unsettle that picture. Erwin Schrödinger then described quantum systems through a wave function, while Max Born interpreted its squared magnitude as a guide to measurement probabilities. Probability had moved from the edge of physics into its foundations. Werner Heisenberg gave uncertainty its most memorable image through the gamma-ray microscope. Shorter wavelength light could locate an electron more precisely, but the scattering photon would produce a larger and less predictable change in momentum. This was an argument about measurement error and physical disturbance. The familiar position and momentum inequality made a different statement. Earl Hesse Kennard derived it rigorously as a restriction on the statistical spreads permitted within a quantum state. Howard Percy Robertson generalized the idea to arbitrary observables, and Erwin Schrödinger strengthened it by including correlations between them. The position and momentum trade-off also emerges from the reciprocal structure of their wave functions. A sharply localized wave packet requires many wavelengths and therefore many momenta. A state with one sharply defined momentum must extend broadly through position. Spin shows that this is not merely a story about photons knocking particles around. A particle can possess a definite spin component along one direction, while producing probabilistic results along another. The uncertainty follows from the incompatibility of the observables, not from an inadequate magnet or an especially rude act of observation. Several different questions therefore hide beneath the single word uncertainty, preparation. Uncertainty concerns the spreads already encoded in a state. Joint measurement uncertainty concerns how accurately incompatible observables can be estimated together. Successive measurement disturbance asks how measuring one quantity changes another. Entropic uncertainty measures limits on prediction through information. Quantum memory shows that entanglement can change how uncertain an observer is, depending on which physical correlations that observer possesses. Masanao Ozawa demonstrated that a simple product of measurement error and disturbance is not universally valid under every definition. Paul Busch, Pekka Lehti, and Reinhard Werner defended different Heisenberg-style trade-offs using more device-based measures. The disagreement did not arise because one group rejected the experimental data. It arose because the word error was being used to answer different operational questions. Entanglement makes a simple classical rescue even harder. Bell tests show that quantum probabilities cannot generally be explained through local objects, carrying complete sets of predetermined answers. Yet those experiments do not force one unique interpretation upon reality. Some physicists accept intrinsic randomness. The many worlds interpretation keeps every outcome in branching components of the wave function. David Bohm's pilot wave theory gives particles definite positions guided non-locally by a wave. Relational quantum mechanics treats properties as definite relative to interactions. Quantum Bayesian approaches interpret probabilities as an agent's expectations. Objective collapse theories propose that the wave function undergoes genuine random physical reductions. These pictures differ profoundly, even when many of them reproduce the same laboratory statistics. Quantum uncertainty is therefore not permission for anything whatsoever to happen. It does not mean nature is vague, careless, or beyond calculation. Quantum mechanics predicts probability distributions, interference patterns, correlations, and experimental bounds with extraordinary numerical accuracy. The uncertainty lies in individual outcomes and in the meaning assigned to the formalism, not in the reliability of the science. Quantum uncertainty may be mathematically exact while remaining conceptually unsettled. Physicists possess firm equations, precise experiments, and several competing accounts of what those equations say the world is actually doing. The limits are clear. What those limits mean is not